What if everything we know about matter, everything that makes up you, me, the stars, and the vast cosmos, is just scratching the surface? What if quarks, the so-called fundamental, building blocks of the universe, aren't fundamental at all? Somewhere beyond the reach of our most powerful telescopes and deepest equations may lie an object so dense, so extreme, and so alien that it breaks the very laws of known physics. These aren't black holes. They aren't neutron stars. There's something far stranger, Preon stars. Hypothetical ultra-dense objects that may be hiding in plain sight, relics of a time before time, made not of atoms, not of quarks, but of something even smaller. Something we've never seen. Something that could rewrite the laws of the universe. Ready to go deeper than anyone ever has? Let's step beyond the edge of the known, into the realm of the impossible, because the truth about Preon stars might just be the missing piece of everything. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Let's start with a chilling thought experiment. Take a sugar cube. Imagine compressing it, not to the density of a neutron star, which is already almost unimaginable, but compressing it thousands, perhaps millions of times more. What would you get? The answer, a preon. A subatomic particle. Smaller than quarks, more fundamental than anything ever observed directly. And now imagine a whole star made up of these. That's the Preon star. A ghost object. A cosmic whisper from an era of physics we haven't yet entered. We've all heard of black holes, the cosmic monsters that devour light itself. We've marveled at neutron stars, with their terrifying density and magnetic fury. But Preon stars? They're not science fiction. They're not even science future. They are science edge. Hypothetical, yes. Speculative, absolutely. But rooted in equations and theoretical frameworks that continue to push the limits of modern particle physics and cosmology. To understand Preon stars, we have to start deep inside the atom. You see, most of us were taught that atoms are made of protons, neutrons, and electrons. Dig deeper, and you learn that protons and neutrons are made of quarks, tiny building blocks that combine in various ways to create the particles we know. But what if quarks themselves aren't the most fundamental particles? What if they are composed of something even smaller? That's where the concept of preons comes in. Introduced in the 1970s as a potential way to explain the bewildering variety of particles in the Standard Model, preons were imagined as the true elementary particles, the ultimate Lego blocks of matter. While still purely theoretical, they offer a seductive solution to one of the biggest headaches in modern physics, the particle zoo. Why are there so many types of particles? Why do they have the masses they do? Why are some stable and others not? Preons could be the answer. But here's the kicker: if preons are real, then under extreme conditions even more intense than inside neutron stars, quarks might break apart into preons. And if that's true, then entire stars might collapse into objects composed entirely of these fundamental particles. Preon stars. Now pause and consider what that means. A preon star would be denser than anything we can currently observe. Smaller than a neutron star of the same mass. Harder to detect than a black hole, because it wouldn't emit the same gravitational waves. It might not even have a strong electromagnetic signature. It could be invisible to every telescope we've ever built. And yet, it could be hiding in plain sight, dark, dense, and ancient. Let's now try to conceptualize the scale of density we're dealing with. A neutron star has the mass of our Sun compressed into the size of a city. That's already absurd. But a preon star? We're talking about compressing that mass further, potentially into an object the size of a football field, or even smaller. The density of such an object would be beyond our current capability to simulate. This isn't just speculation for fun, it's a roadmap toward the very limit of matter. And here's where the theory turns even more provocative. According to some physicists, preon stars may have formed in the early universe, within microseconds after the Big Bang, when temperatures and pressures were unimaginably high. While the early universe was a chaos of energy and emerging particles, there may have been pockets of matter so hot, so compressed, that they didn't form quarks. they went straight to preons. And if those conditions held, even briefly, preon stars may have been born. Not as a fluke, but as a common outcome of the early cosmos. These objects would be older than any star, darker than any black hole, and more stable than any atom. They could still be drifting silently through the intergalactic void, unseen, undetected, unacknowledged. They wouldn't emit radiation. They wouldn't glow. They might not even bend light the way black holes do. But they would exist, and in doing so, they would be the most exotic form of matter in the universe. Now let's pull back for a second and ask a crucial question. How do we even begin to look for something we can't see? That's one of the greatest challenges in the study of preon stars. They might not interact with light. They might not even behave like traditional matter. But there are clues. Subtle clues. For one, gravitational lensing. If a preon star were to drift between us and a distant object, it could bend light in subtle ways, just enough to give itself away. Second, gravitational waves. If a preon star were to collide with another massive object, the resulting waves in spacetime might have a unique signature, different from the chirp of two black holes or neutron stars colliding. Finally, dark matter. Some physicists believe that preon stars, or preon-like objects, might explain at least part of the mystery of dark matter. Their invisible nature and extreme density make them perfect candidates. And this is where things get even wilder. Imagine this. Preon stars might not just be hiding in intergalactic space. They might be orbiting our own galaxy. They might even be passing through our solar system, undetected. No light. No sound. No warning. Just silent witnesses to a deeper reality we have yet to grasp. Theoretical physicists have tried to model what preon matter would look like. The equations are complex, but the general consensus is that if preons exist, they would form a degenerate gas similar to the one inside white dwarfs and neutron stars, except composed of entirely new types of particles. The forces holding a preon star together would be incomprehensibly strong, likely orders of magnitude stronger than the strong nuclear force that binds quarks. And that's not just fascinating, it's terrifying. Because if those forces were ever unlocked, if a piece of preon matter were to interact with ordinary matter, it could potentially release more energy than a supernova. It could be the ultimate weapon, the final energy source, or even the end of everything. But let's not leap too far into apocalyptic speculation. For now, we're still trying to prove they exist at all. And the hunt is on. Particle physicists are designing experiments at high-energy colliders to look for hints of substructure within quarks. Astrophysicists are scanning the cosmos for anomalous gravitational effects. And theorists are pushing the boundaries of quantum field theory, string theory, and even holographic models of the universe in search of answers. Preon stars represent not just a new kind of object, but a new kind of question. A question about the ultimate nature of matter, the limits of compression, and the unseen architecture of reality itself. What if we've already detected preon stars without realizing it? Some of the unexplained microlensing events observed in the 1990s and early 2000s might have been caused by dense, compact objects that didn't fit any known profile. Some gravitational wave detections don't perfectly match black hole or neutron star models. Could these be the fingerprints of preon stars? Could we be staring at ghosts, unable to recognize what they are? The truth is, preon stars lie at the intersection of two of the most ambitious goals in physics: unifying quantum mechanics and gravity, and understanding the true nature of dark matter. They represent a hypothetical fusion of particle physics and cosmology, an object that requires us to know everything before we can see anything. They are the edge of the map. The question mark at the end of physics. They are science waiting to happen. They exist right on the knife's edge between the known and the unknowable. Theoretical, yes, but not impossible. And in a universe as vast and ancient as ours, the improbable happens more often than we'd like to admit. If preon stars are real, they would be the smallest and most extreme stars to ever exist. Yet no telescope, no satellite, no gravitational wave detector has definitively found one. Not because they don't exist, but because they could be hiding in plain sight, so small and so faint that they slip past our instruments like shadows in the dark. To understand Preon stars, we have to peel back the layers of matter itself. The first layer is atoms, the basic building blocks of ordinary matter. Atoms are mostly empty space, with a dense nucleus surrounded by a cloud of electrons. Dig deeper into the nucleus and you find protons and neutrons, themselves made of even smaller particles, quarks. And here's where it gets speculative. For decades, scientists have asked, what if quarks themselves aren't the end of the line? What if they're made of something even more fundamental? That's where preons come in. Preons are hypothetical particles proposed to be the building blocks of quarks and leptons. If quarks are the alphabet of matter, then preons are the individual brush strokes behind each letter, more granular, more elemental, and possibly more powerful than anything we've ever known. They haven't been discovered in any collider yet, but their existence could solve several mysteries in particle physics, such as why particles come in different flavors, or why the masses of fundamental particles seem so arbitrary. Preons could unify the Standard Model in a way no other theory has. Now imagine a situation in the universe where pressure becomes so intense, so unbelievably forceful, that not even quarks can resist. The structure holding them collapses. Protons and neutrons dissolve. What remains? Preons, compressed into a volume so tiny, the resulting object is smaller than a city block yet more massive than Earth. This would be the birth of a preon star. Unlike black holes, preon stars might not collapse into singularities. Instead, they could hover just shy of that ultimate fate, ultra-dense, ultra-compact, but still maintaining a physical surface. They might be mistaken for small neutron stars, or perhaps not seen at all. But their theoretical signatures could differ, perhaps in their gravitational pull, their interactions with dark matter, or their role in the formation of the early universe. Their formation is just as fascinating as their existence. When a massive star reaches the end of its life, it undergoes a supernova explosion. If the mass of the core is high enough, it collapses into a neutron star. Add even more mass, and you get a black hole. But some physicists believe that under certain conditions, extreme symmetry, exotic matter configurations, or quantum corrections, a collapsing core might pass through the neutron state but stop short of forming a black hole. It could instead stabilize as a preon star. This leads us to a provocative possibility. Some of the objects we currently classify as black holes might actually be preon stars in disguise. Unlike black holes, which trap light beyond their event horizon, preon stars might have no such boundary. They might appear dark, yet still emit tiny, strange bursts of energy, perhaps through quantum tunneling or anomalous particle emissions. And that's where it gets thrilling. We might have already seen hints of preon stars, but we didn't know what we were looking at. From here, we spiral deeper into the unknown. Preon stars could serve as natural laboratories for physics beyond the Standard Model. They might help explain dark matter, which makes up roughly 85% of the matter in the universe but has never been directly observed. Some theories suggest that dark matter could consist of stable preon-based configurations, massive, invisible, and weakly interacting. If so, then entire halos of dark matter around galaxies might actually be massive clouds of ancient, cold preon matter. They could also change how we think about gravitational waves. Most of the gravitational waves we've detected come from merging black holes or neutron stars. But what if two preon stars collided? The resulting wave signature might be subtly different, slightly less massive, slightly more abrupt, and maybe containing echoes of higher-order quantum effects. These could be hiding in the data already collected by LIGO and Virgo, waiting for someone to look at them with the right lens. But we have to ask, if preon stars exist, where are they? Why haven't we found them? The answer may lie in their size and density. A typical neutron star is already just about 20 kilometers wide. A preon star might be the size of a marble. Think about that, a cosmic object with more mass than a planet, shrunk down to something that could fit in the palm of your hand. Our current methods of astronomical detection simply aren't designed to find something that compact unless it interacts dramatically with its surroundings. A preon star in isolation could go unnoticed for billions of years. And maybe that's exactly what has happened. The different types of fundamental particles, their seemingly arbitrary masses, and the structure of their interactions all hint at a deeper layer beneath the standard model. Preons could be the key to this hidden framework. They might be the true bedrock of the universe, the smallest, most indivisible units of existence. If that's the case, then compressing matter beyond the limits of neutron degeneracy pressure could force quarks to dissolve into preons, giving birth to an entirely new kind of star. Such a star would form under conditions far more extreme than those required to produce a neutron star. In a dying massive star, if the core's gravity becomes strong enough to overcome the forces keeping quarks bound within neutrons and protons, the matter could collapse past the neutron phase. This is where theoretical physics diverges into the unknown. In one branch, we get a black hole. But in another, more exotic possibility, we get a Preon star. Unlike black holes, Preon stars wouldn't necessarily collapse into a singularity. They could be supported by an entirely new form of degeneracy pressure, one stemming from the behavior of preons themselves. This pressure would prevent total collapse, creating a stable, yet unimaginably dense object. And this object would be incredibly small, perhaps no bigger than a grain of sand, yet heavier than Mount Everest. The size-to-mass ratio of a Preon star would be staggering. To an outside observer, such a star might appear almost like a black hole, but it wouldn't have an event horizon. Light could still escape from it, albeit extremely redshifted. It wouldn't exhibit the same kind of Hawking radiation or gravitational behavior that a black hole does. In fact, it might masquerade as a neutron star or even be mistaken for a primordial black hole, those tiny black holes thought to have formed in the early moments of the universe. Because of their potential size and mass, Preon stars could be some of the most deceptive objects in the cosmos. If they exist, they may be lurking right now in our own galaxy, hiding within datasets collected by astronomers who assumed they were seeing something more ordinary. Our inability to detect them may not be due to their absence, but due to our assumptions. We have never designed our instruments or our theories to look for something like this, because we've never been certain it was even possible. The creation of a Preon star may also offer clues to one of the deepest mysteries in astrophysics: the nature of dark matter. Dark matter makes up about 27% of the universe, yet we have no idea what it is. We can't see it, we can't touch it, and we can't directly detect it, only infer its presence through its gravitational effects. Some scientists have speculated that if Preon stars exist, they could form a significant component of dark matter. These stars, if abundant, could provide the missing mass we've been searching for, cloaked in shadows and silence. Even more fascinating is the potential age of Preon stars. Unlike neutron stars or black holes that form from dying stars, Preon stars might have formed in the earliest moments after the Big Bang. In the infant universe, conditions were chaotic and extreme. Temperatures and densities were so high that ordinary matter could not exist. In those first few seconds, pockets of high-density fluctuations may have allowed quark matter to transition into Preon matter, forming tiny yet massively heavy objects. These ancient relics would have wandered the cosmos for over 13 billion years, unchanged, undetected. Their longevity could make them cosmic time capsules. If we could find one, study it, and understand it, we might uncover secrets not just about preons themselves, but about the conditions of the early universe. It's a direct line of evidence into epochs otherwise unreachable by any experiment or telescope. Preon stars may be the fossils of the Big Bang, drifting silently across the void, holding within them the earliest whispers of creation. The theoretical modeling of Preon stars is not without its difficulties. The physics of such objects goes beyond the standard model, beyond quantum chromodynamics, and into uncharted theoretical territory. To describe how preons behave, how they interact, and how they form matter requires mathematical frameworks we are only beginning to explore. Various preon models have been proposed over the decades, ranging from simple binding schemes to complex lattice structures, but none have yet achieved universal acceptance. This is largely because, without experimental data, theory remains speculation. But that hasn't stopped scientists from trying. One of the more compelling reasons to believe in the possibility of preon stars comes from the limitations of current models. The Standard Model, though highly successful, has notable gaps. It does not explain gravity. It cannot account for the mass of neutrinos. It offers no insights into dark energy or the matter-antimatter asymmetry in the universe. If preons exist, and if preon stars can form, then they may help to bridge these gaps, offering a route to a more unified understanding of fundamental physics. In some speculative frameworks, preons aren't just the foundation of matter, they are the quantum threads that weave the entire universe. In these models, space-time itself may emerge from preon interactions, suggesting that by studying them, we could unlock the secret not just of matter, but of reality itself. If that's the case, then preon stars are not just cosmic curiosities. They are the Rosetta Stones of the universe, dense, dark, and encoded with the language of existence. The light emitted from the surface of a preon star would be so severely redshifted due to its intense gravitational field that it would be nearly impossible to detect using current astronomical instruments. Despite their elusiveness, preon stars would still exert gravitational influence. Their presence could be inferred not through the light they emit, but through the effect they have on surrounding matter and space-time. A preon star might drift silently through a star system, undetectable by light, but betraying its existence by the way it bends the light from distant stars behind it. This effect, known as gravitational lensing, is one of the most powerful tools astronomers have to find dark or invisible mass in the universe. A star orbiting an unseen partner that has an extreme mass but no corresponding light source might also be a clue, one that doesn't match a black hole, neutron star, or white dwarf. In such a case, the unseen object might be a preon star. The possibility that we've already observed such anomalies, misclassified or misunderstood, adds an eerie sense of realism to the theory. Perhaps what we've thought were strange pulsars or invisible black holes were, in fact, preon stars all along. If they do exist, then they may also serve as relics from the early universe, compact fossils from a time when the cosmos was hot, dense, and chaotic enough to allow the formation of preon matter. Such objects would be older than the oldest stars, remnants of the first microseconds after the Big Bang. During this era, the universe was so dense that ordinary particles hadn't yet formed. In that primordial plasma, if preons existed, they would have dominated. It's entirely possible that, before atoms, before quarks, before protons and neutrons, small dense pockets of preon matter condensed, survived, and drifted through cosmic time mostly unchanged. These ancient remnants would have withstood supernovae, galactic collisions, and cosmic radiation storms. They would be virtually indestructible, shielded by their own internal pressure and protected by their microscopic size. They could even pass through planets and stars without leaving a trace, undisturbed and unobservable. It is conceivable that a preon star might pass through Earth one day, and we wouldn't even know it. This brings us to an unsettling realization. The universe may be filled with these ghost stars, ancient, silent, and invisible. They might float through galaxies, slip through the hearts of suns, and lie undetected in the shadows of gravitational fields. Their existence would change our understanding of stellar evolution, of the early universe, and of the very nature of matter itself. Detecting one would be more than a scientific breakthrough, it would be a paradigm shift. It would be proof that quarks are not the most fundamental particles, that there is more beneath the surface of the Standard Model, and that we are only beginning to scratch the surface of the true architecture of the cosmos. To begin searching for these objects, scientists have proposed using high-precision gravitational lensing surveys, sensitive enough to detect even small fluctuations in light caused by tiny but massive bodies. Additionally, there's potential in studying gravitational waves. If a preon star were to collide with another compact object, a neutron star for instance, it could produce a unique gravitational wave signature, distinct from known mergers. These fingerprints in spacetime could help distinguish preon stars from black holes or other dense remnants. Another path toward discovery lies in particle accelerators. Though we have not observed preons directly, if they do exist, then future accelerators, far more powerful than the Large Hadron Collider, might reach energies high enough to reveal them. Discovering a preon would lend immediate credibility to the theory of preon stars. It would offer the missing particle in the puzzle and allow us to reverse engineer the physical laws that govern these ultra-dense objects. In theory, Preon stars could also offer answers to other unsolved mysteries in physics. Dark matter, for instance, remains one of the biggest enigmas in cosmology. Some researchers have suggested that compact, invisible Preon stars might account for a portion of dark matter. They're massive, undetectable by light, and would be spread sparsely across the universe, making them ideal dark matter candidates, at least in part. Furthermore, they could help refine our understanding of quantum gravity. In the transition between neutron stars and black holes, there exists a gap, an unclear region where classical physics starts to break down but quantum gravity hasn't taken over completely. Preon stars might reside in this narrow window, acting as a natural laboratory for new physics. By studying them, we might uncover insights that bridge general relativity and quantum mechanics. Some theorists have even proposed that Preon stars might be tied to extra dimensions. In certain models of the universe, particles like preons may originate from higher dimensional space. If this is true, Preon stars could represent physical manifestations of higher dimensional effects, compressed into our three-dimensional universe. This would give us a direct, albeit indirect, glimpse into dimensions we cannot otherwise see. The speculative nature of Preon stars does not diminish their significance. All scientific revolutions begin with speculation, followed by prediction, then evidence. The idea of black holes was once theoretical. So were neutron stars. Even the atom was once an unprovable concept. Today, they're all cornerstones of our understanding. Preon stars may be the next rung on that ladder, one that pushes us to rethink the limits of density, structure, and what it means to be fundamental. The search for Preon stars is more than a quest to find a new type of object. It's a journey into the fabric of the cosmos, a challenge to our assumptions about what matter is and what it can become. If we find even one, it would be like finding a needle in a cosmic haystack. But that needle would be older than time itself, denser than anything we've ever known, and more mysterious than any black hole. These relics would not only be ancient but extraordinarily rare. The conditions required to form a Preon star would have been vanishingly rare even in the extreme environment of the early universe. Unlike ordinary stars that form from clouds of hydrogen gas, Preon stars would need a highly specific set of physical circumstances, extreme densities, immense temperatures, and an environment where quarks are no longer the end of the line, but merely transitional structures. If these stars truly formed in the early cosmos, they would have persisted, largely unchanged, throughout cosmic history. Because they are so stable, so dense, and so resistant to interaction, they would have survived the chaos of galactic formation, the supernovae of neighboring stars, and the radiation storms of ancient quasars. Preon stars would be scattered across the universe like cosmic time capsules, their interiors preserving a state of matter that has not existed since the dawn of time. Despite their invisibility, their influence might be hiding in plain sight. When we look at the universe and detect unexplained gravitational anomalies, movements of stars, lensing effects, or dark clumps where no visible matter exists, we may be seeing the gravitational fingerprints of Preon stars. Their presence could explain some of the mysterious behavior we've long attributed to dark matter. Though they may not account for all of it, clusters of Preon stars and galactic halos could contribute to the missing mass that affects galactic rotation curves. The very notion that such small, dense objects could have survived for billions of years forces us to rethink our understanding of stellar evolution. Every textbook description of how stars live and die might be incomplete without considering these exotic anomalies. In standard models, the endpoint for massive stars is usually a neutron star or black hole. But what if the spectrum of stellar remnants includes something more? Something that forms only under conditions of unimaginable pressure, where the very identity of matter dissolves into something stranger than we've ever seen. It's this possibility that has intrigued theorists and astrophysicists for decades. But the quest to prove or disprove the existence of Preon stars faces immense challenges. Unlike neutron stars or black holes, which emit detectable radiation or gravitational waves during violent mergers, Preon stars could pass through space almost entirely mute. Their mergers might not produce the same signals, or might release energy in forms we haven't yet learned to measure. Their silence doesn't imply absence, it might mean we're just not listening the right way. Even if we could detect one, identifying it as a Preon star would be even harder. Theoretical models suggest they would be smaller and denser than neutron stars, but without direct observation or a distinct, unique signal, confirming their existence remains speculative. Some researchers have proposed looking for Preon stars by studying the aftermath of neutron star collisions. If, in rare cases, these collisions fail to produce a black hole and instead result in a stable, ultra-dense object with unusual properties, it could hint at the formation of Preon matter. Another possibility lies in high-energy cosmic ray detection. If Preon matter occasionally breaks apart in space, it might produce a very specific signature of particle decay, one that cannot be explained by known physics. Searching for such anomalies in particle showers from deep space could offer indirect evidence for the existence of preons, and by extension, Preon stars. However, these signatures would be incredibly rare, buried in noise, and difficult to interpret without precise theoretical predictions. Some theories go even further, proposing that Preon stars might not just be relics of the past, but still forming today under extreme conditions. For instance, in the aftermath of a supernova where the core collapse is incomplete, or in scenarios where quark stars undergo additional compression, matter might squeeze into a Preon state. Such a transition would represent a new phase of matter, not unlike how water transitions into ice or steam, but on an entirely different scale of density and energy. If such a transition occurs, it might release an enormous amount of energy, perhaps even creating a unique type of gamma-ray burst or an exotic form of neutrino emission. These are the kinds of signals astrophysicists are now beginning to explore, searching databases of cosmic events for anomalies that could point to something beyond our current models. The hope is that, eventually, these breadcrumbs will lead us to the unmistakable footprint of a Preon star. These exotic anomalies challenge our understanding of cosmic death, transformation, and rebirth. When a star exhausts its nuclear fuel, we typically categorize its fate along predictable lines: white dwarfs, neutron stars, or black holes. But if Preon stars are possible, then there's a secret, hidden pathway. A quantum tightrope walk that occurs only under the most extreme pressures and densities, leading not to destruction or complete collapse, but to transformation into something far stranger than we've ever directly observed. What makes this idea so alluring is not just the strangeness of the object itself, but the window it opens into deeper layers of reality. If we ever confirm the existence of a Preon star, it would immediately validate the Preon hypothesis and suggest that everything we've labeled as fundamental may, in fact, be composite. Our current model of the universe, based on quarks and leptons as indivisible building blocks, would unravel, revealing a deeper level of substructure, with new physics, new forces, and new symmetries yet to be discovered. Preon stars also raise philosophical questions about the nature of matter, stability, and the boundaries of the observable universe. Could there be even smaller building blocks within the preons themselves? Are we witnessing an infinite regress of structures, each revealing a deeper, smaller component the closer we look? The existence of Preon stars wouldn't just suggest a new type of star, it would imply a recursive, fractal-like depth to reality, with each layer more alien and beautiful than the last. The mathematical models that attempt to describe these stars are some of the most extreme and exotic in all of theoretical astrophysics. They involve pressure and energy densities that exceed anything ever created in a laboratory or observed in nature. They stretch the equations of general relativity and quantum field theory to their breaking points. The core of a Preon star would be a place where space-time itself is warped almost beyond recognition, an arena of unimaginable curvature, where time dilates, space contracts, and energy becomes almost inseparable from geometry. Despite this, the equations suggest that such stars might be stable. Unlike black holes, which inevitably collapse into singularities, or so we think, Preon stars could find an equilibrium, suspended between collapse and expansion by a new form of degeneracy pressure arising from the quantum properties of preons themselves. This would be a new kind of stability, one that no current particle accelerator has ever replicated, but which might naturally occur in the cosmos. some theoretical models propose that the mass range of Preon stars could vary significantly. On the low end, they might weigh just a few Earth masses, but be only millimeters across, almost impossible to detect without direct gravitational lensing. On the high end, they could approach the lower limit of stellar black hole mass, and yet still resist collapse. In fact, one of the more fascinating proposals is that some black holes we think we've observed might not be black holes at all. They might be massive Preon stars that mimic many of the same gravitational effects, but without forming a singularity or event horizon. This raises an observational challenge. How would we tell the difference? From a distance, a black hole and a massive Preon star might look almost identical. They'd have similar gravitational pulls, they might bend light similarly, and they might even produce similar gravitational wave signatures and mergers. But there are subtle differences. A Preon star wouldn't have an event horizon, meaning in theory, it could emit faint radiation or reflect particles in a way a black hole never could. A very precise observation of the way light bends around such an object, called strong gravitational lensing, might reveal tiny deviations that expose the truth. Even more tantalizing is the possibility that some fast radio bursts, FRBs, gamma-ray bursts, or other high-energy cosmic phenomena might originate from interactions involving Preon stars. Perhaps two Preon stars colliding could release a unique signature, one that we've observed but failed to recognize for what it was. Or maybe when a neutron star collapses under the right conditions, instead of becoming a black hole, it becomes a Preon star, emitting a unique burst of particles or gravitational waves that future observatories could detect. These events might be so rare, so subtle, that it would take decades of focused observation just to catch one. But in that moment, the entire landscape of astrophysics would shift. We would finally know, not only are preons real, but nature has found a way to assemble them into stable, enduring structures, miniature monuments to the deepest secrets of the quantum world. And what about the interiors of these objects? In a neutron star, we believe the matter is crushed so densely that neutrons are packed together like a degenerate gas. But in a Preon star, that structure breaks down entirely. There would be no neutrons, no protons, no atoms at all, just a superfluid, superdense ocean of preons. The pressures inside would be so intense that even the vacuum state of space might be altered. Quantum fluctuations could behave differently. The very constants of nature might shift ever so slightly in such an environment, making a Preon star not just dense, but deeply alien. This also raises the question of how Preon stars interact with other forms of matter and energy. Would they absorb normal matter like black holes? Would they interact weakly, like dark matter? Or might they occasionally flare with strange quantum bursts when they encounter high-density environments? Could they be mined, or would any contact with them result in catastrophic destabilization? We simply don't know, but every model suggests they would be among the most inert and isolated objects in existence, unlikely to merge with or consume matter in the same way black holes do. And if we ever did get close to one, say, by detecting one passing through our solar system, it would likely be nearly invisible. There'd be no light, no radio waves, no X-rays. Just a tiny, relentless distortion in local gravity. Clocks would tick a little slower. Satellites might drift ever so slightly. And if it passed through a planet, it could punch a microscopic tunnel straight through, leaving barely a trace, except for the gravitational fingerprint it etched into the planet's orbit. One of the most difficult challenges in modeling Preon stars lies in the lack of direct observational evidence for preons themselves. Since preons are hypothetical particles, no particle accelerator has yet detected them, and their theoretical properties vary depending on the specific preon model being considered. This means that any attempt to describe how preon stars form, evolve, or behave must rely on speculative physics, educated guesses that extrapolate far beyond our current experimental capabilities. Nevertheless, scientists have constructed various theoretical frameworks that explore what a preon star might look like if it existed. For example, calculations suggest that a preon star would be far smaller and denser than a neutron star of the same mass. Imagine compressing an entire mountain into a space the size of a raindrop. That's the kind of density we're talking about. The matter inside such a star would not consist of atoms, or even nuclei, but of individual preons packed together in configurations so tight that they form what might be the most stable state of matter in the universe. These preon configurations, sometimes called preon condensates, would resist further collapse through quantum degeneracy pressure or other exotic forces yet to be fully understood. They might form shells or layers of different preon combinations, or exist as a quarkless soup of ultra-fundamental particles suspended in a sea of quantum fluctuations. The surface of a preon star, if it can be said to have one, would be a bizarre boundary, smooth, sharp, and impenetrable, where space and time behave differently than in the surrounding vacuum. What's truly mind-bending is the suggestion that some black holes we've detected may not be black holes at all, but ultra-dense preon stars masquerading as them. If preon stars exist, they might offer a resolution to the information paradox that has haunted black hole physics for decades. Unlike black holes, which theoretically allow no escape from their event horizon, preon stars could possess a physical surface, an actual, tangible boundary just shy of where an event horizon would form. In this scenario, matter falling onto a preon star wouldn't be irretrievably lost to a singularity. Instead, it could interact with the ultra-dense surface, potentially leaving behind traces or radiation that encode the information of what was absorbed. This idea aligns with some of the proposed alternatives to black holes, such as gravastars or fuzzballs, where the singularity is replaced by something else, an object with finite density and complex quantum structure. Preon stars would fit into this family of exotic, horizonless compact objects that preserve unitarity in quantum mechanics while explaining many of the observational effects previously attributed to black holes. Of course, distinguishing between a black hole and a preon star is not an easy task. From a distance, their gravitational fields might be nearly indistinguishable. The only way to tell them apart could be through subtle variations in emitted radiation or gravitational waves during extreme astrophysical events like mergers or close encounters with other stars. Some theorists suggest that a preon star, lacking a true event horizon, might produce unique signatures during collisions, perhaps bursts of energy, or resonances that current detectors are just beginning to have the sensitivity to pick up. With instruments like the Event Horizon Telescope and the LIGO/Virgo/Cagra gravitational wave observatories, we are entering a new era where these subtle differences could become observable. If an object believed to be a black hole behaves just slightly off-script, emitting echoes and gravitational waves, or producing unexpected electromagnetic afterglows, then it might hint at something more exotic beneath the veil. Something that is not quite a black hole, but also not any star we've ever known. And that brings us to one of the most thrilling implications of all. If preon stars exist now, they may have been around since the birth of the universe. That means they could be scattered throughout space, silent and invisible, waiting to be discovered not by telescopes, but by their effects. Their gravitational pull, their interactions with surrounding matter, or their role in galactic evolution might offer the first glimpses of a hidden cosmic population that has eluded us entirely, until now. Preon stars could also reshape our understanding of cosmology and the early universe. If preons exist and can form stable matter under extreme conditions, it's possible that these objects were forged in the moments just after the Big Bang, when the universe was unimaginably hot and dense. In those first fractions of a second, before quarks had even coalesced into protons and neutrons, preons may have clustered into compact knots of matter, seeds of preon stars that drifted through space as the universe expanded. These primordial preon stars would be ancient relics, older than any neutron star or galaxy, silently floating in the cosmic dark. They might outnumber black holes, yet remain invisible due to their size and lack of strong electromagnetic emissions. If this is true, preon stars could be an unrecognized component of dark matter, the invisible mass that makes up about 85% of the universe but has never been directly observed. While most dark matter candidates are exotic particles like WIMPs or axions, massive compact halo objects, machos, such as preon stars provide an alternative explanation. Perhaps the darkness comes not from strange particles, but from strange objects. This opens an entirely new frontier in observational astronomy. Detecting these elusive stars may require us to rethink how we search the sky. Traditional telescopes look for light, but Preon stars may emit none. Instead, scientists are now exploring gravitational microlensing, watching for tiny distortions in the light from background stars, caused by the gravity of a passing massive object. If a Preon star drifts in front of a distant star, its intense gravity could bend the starlight, producing a brief but measurable amplification. Multiple such events could reveal a population of invisible, ultra-dense objects lurking in the galactic halo. Such discoveries would be revolutionary. Not only would they confirm the existence of a new class of stellar object, but they would also provide critical insights into the composition of the universe itself. Every Preon star detected would be like finding a fossil from the very beginning of time, evidence that the early universe was far stranger and more varied than we've imagined. But beyond their role in cosmology and dark matter, Preon stars might also influence our theories of particle physics at a fundamental level. If preons exist and can be packed into stable configurations, it implies new forces or interactions that bind them, forces beyond the four fundamental ones we currently recognize: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. This would demand the introduction of an entirely new force of nature, sometimes called the Preon binding force, with its own carrier particles and equations. Developing a theory around such a force requires an extension of the standard model of particle physics, likely through a grand unified theory, GUT, or a more exotic framework like string theory. Some models propose that preons are actually manifestations of vibrating strings or branes in higher dimensional space, and that what we call quarks and leptons are just different vibrational modes. In this view, a Preon star would be a tightly wound knot of extra-dimensional geometry, a literal wrinkle in the fabric of reality. These are not just abstract mathematical concepts, they carry real implications for the energy scales accessible to our technology. If preons exist and are bound by forces stronger than the strong nuclear force, creating or probing them would require energies far beyond what the Large Hadron Collider can produce. Some theorists argue that only astronomical events, supernovae, neutron star collisions, or the Big Bang itself, reach the energy levels required to manifest preon matter. This makes cosmic phenomena not just important for astrophysics, but for particle physics as well. The universe becomes a natural laboratory, and stars like these are its ultimate experiments. Moreover, if we could ever isolate preon matter, an endeavor currently beyond imagination, we might unlock entirely new technologies. The energy densities involved are so high that even a tiny amount of preon material could store more energy than any nuclear fuel. This leads to speculation about preon bombs, or other exotic energy sources that lie squarely in the realm of science fiction for now, but that could become possible if we master the manipulation of such fundamental structures. Of course, this also raises questions about the stability of preon matter. Could it decay? Would exposure to it trigger runaway reactions? Would it be safe to even approach such an object? Theoretical physicists are only beginning to scratch the surface of these questions. What we do know is that if preon stars exist, they are likely the most compact and stable matter structures in the universe, stable enough to survive cosmic timescales, yet exotic enough to challenge every assumption we've made about matter, energy, and space-time. In addition to microlensing, gravitational wave astronomy offers another promising path. When two ultra-dense objects spiral into each other and collide, they generate ripples in the fabric of space-time, gravitational waves, that can be detected by instruments like LIGO and Virgo. While these waves have been observed from neutron star and black hole mergers, a collision involving preon stars might produce a distinct gravitational wave signature. Due to their smaller size and higher density, preon stars could merge more quickly and with different frequency patterns compared to traditional compact objects. The analysis of these waveforms, especially in the moments just before and after a merger, could reveal deviations from expected models. For instance, a lack of post-merger black hole formation, or an unexpected echo in the waveform, might suggest the presence of an exotic object with a surface rather than an event horizon. If we were to detect such a signal, it wouldn't just be a landmark moment in astrophysics. It would be direct, physical evidence of an entirely new state of matter. But the implications of Preon stars go beyond exotic astrophysical events. They force us to rethink the very fabric of matter itself. For centuries, physicists have searched for the most fundamental constituents of reality. From atoms to electrons to quarks, each layer we've peeled back has revealed something smaller, something deeper. Preons, if they exist, would be the next step in this journey, particles that form the foundation of all known matter. And just as the discovery of quarks transformed nuclear physics, the confirmation of preons would trigger a revolution in particle physics and cosmology alike. Some models even suggest that preons aren't particles in the traditional sense but are instead manifestations of even more fundamental strings or quantum fields. This blurs the line between particle physics and string theory, hinting at a unified framework that describes everything from the smallest scales to the vast structure of the cosmos. Preon stars, then, would be more than just dense balls of exotic matter. They could be cosmic laboratories where the laws of nature push past our current limits and reveal the architecture of reality itself. And yet, for all their potential, Preon stars remain ghosts in our theoretical machinery, ever present in equations, simulations, and hypotheses, but still unseen in the sky. This is the paradox that makes them so irresistible. They could be all around us, hiding in plain sight, influencing the motion of galaxies and the expansion of the universe, yet evading every direct attempt at detection. To consider that Preon stars might exist, we must also consider what else must be true. The standard model of particle physics would need to be incomplete, not incorrect, but a stepping stone to a deeper truth. Supersymmetry or other grand unified theories would likely come into play, proposing that particles we once thought were fundamental are in fact composites of even smaller constituents. This would challenge decades of experimental results and call for new, more powerful accelerators capable of probing deeper into the fabric of matter. Physicists have proposed several models of preon composition, each with its own implications for the structure of preon stars. In some theories, quarks and leptons are made from just 2 or 3 kinds of preons, bound together by forces stronger than the strong nuclear force. These preons may carry new types of charge or interact through undiscovered fields. If these interactions produce attractive forces at high energy densities, they could naturally form stable lumps, preon stars, that are resilient against collapse and capable of existing for billions of years. Such stars could range in size and mass, just like their neutron and black hole cousins. Some might be stellar remnants left behind by the death of massive stars, while others could be primordial, forged in the earliest instance of the universe. There might even be a spectrum of compact objects, with neutron stars on one end, black holes on the other, and preon stars occupying the mysterious middle ground. Each type would have its own defining characteristics, mass thresholds, density profiles, temperature behavior, but all would share one crucial trait: the defiance of conventional physics. Even the question of how preon matter behaves under pressure remains an open mystery. Unlike neutron matter, which can be modeled using quantum chromodynamics and nuclear physics, preon matter exists in a regime that defies our current tools. Its behavior would depend on forces we have yet to understand, mediated by particles we have yet to detect. It might be superfluid, superconducting, or something beyond either concept, a new state of matter where the rules of thermodynamics, gravity, and quantum mechanics intertwine in strange and beautiful ways. This speculative freedom has given rise to bold ideas. Some researchers have suggested that preon stars could support stable exotic phenomena on their surfaces, fields or particles that can only exist in the presence of extreme energy densities. Others have proposed that the interaction between preon matter and conventional matter could produce detectable radiation or magnetic anomalies. There's even a hypothesis that certain fast radio bursts, FRBs, mysterious millisecond-long pulses detected from deep space, could be the result of sudden phase transitions in preon star interiors, brief flashes from the collapse or reconfiguration of preon condensates. Though none of these theories have been confirmed, they all point toward one truth: preon stars, if real, would not merely be new kinds of stars. They would be keys to unlocking questions that stretch across the cosmos and deep into the heart of matter itself. Their existence would reshape our models of stellar evolution, gravitational collapse, and the early universe. They would redefine what it means for something to be fundamental. And in doing so, they would bring us closer to a unified understanding of the universe. Before any of this can happen, the very existence of preons, and by extension, preon stars, must be proven. This is where experimental physics, astrophysical observation, and particle accelerator research converge. Facilities like the Large Hadron Collider have been instrumental in testing the boundaries of the Standard Model. While it hasn't directly detected preons, the search continues, especially in the form of high-energy collisions that could reveal substructures within quarks and leptons. Some researchers argue that future colliders, with even greater energy scales, might be necessary to probe deeply enough to detect preonic behavior. The proposed Future Circular Collider, FCC, and the International Linear Collider, ILC, could be key players in this endeavor. These machines aim to reach energy levels and precision that might uncover deviations from current particle models, deviations that could hint at preonic substructure. By smashing particles together at unimaginable velocities and carefully analyzing the debris, scientists hope to observe anomalies in the scattering patterns or decay rates that defy the predictions of the Standard Model. In parallel, theorists are developing increasingly sophisticated mathematical models to describe how preons might behave, interact, and combine to form the particles we already know. These models aim to reconcile the preon concept with existing quantum field theories and possibly even with string theory or loop quantum gravity. If a consistent, testable theory of preons emerges that explains the observed particle spectrum and their properties more elegantly than the current model, it would be a monumental paradigm shift. Meanwhile, astrophysicists continue scanning the skies. The potential discovery of preon stars would lend enormous weight to the preon hypothesis. Unlike in laboratory settings, nature might already have the conditions required to compress matter into such extreme forms. The detection of objects with masses between that of neutron stars and black holes, but without the corresponding gravitational signatures of black holes, would be a strong indicator. Especially if these objects exhibit unusual thermal emissions, radiation patterns, or timing behaviors, such as from pulsars that suddenly change spin or brightness. It's also worth noting that preon stars, if they exist, might influence cosmic evolution on grand scales. Imagine millions of preon stars scattered throughout the early universe, subtly affecting the distribution of matter, the rate of galaxy formation, or even the shape of cosmic filaments. They could play a role in seeding black holes or act as gravitational anchors for dark matter clumps. Their influence could be so quiet yet so pervasive that we've mistaken them for something else, or missed them altogether. Some theories even propose that preon stars could explain certain unexplained gamma-ray bursts or fast radio bursts. These mysterious, powerful signals flash across the sky with no clear origin. If preon stars collide or undergo internal structural shifts, they might release bursts of energy unlike anything else. These outbursts could serve as cosmic fingerprints, pointing toward an exotic origin rooted in physics we don't yet fully understand. The search for such signals is ongoing. Radio telescopes like CHIME and the Square Kilometre Array are mapping the sky with unprecedented sensitivity and breadth. Their datasets, when cross-referenced with gravitational wave detectors, X-ray observatories, and infrared telescopes, may uncover correlations that suggest a new class of stellar object. And if preon stars are found to cluster in certain regions, or if their formation appears linked to specific types of supernovae, we could begin to trace their life cycles and evolution. The potential implications reach even further. If preons are indeed more fundamental than quarks and leptons, it could mean that the so-called constants of nature, such as the strength of the strong force, the masses of fundamental particles, or the speed of light, might not be constant at all. They could vary depending on the structure and arrangement of preons in a given region of the universe. This would revolutionize our understanding of physics, cosmology, and even the possibility of a multiverse where different regions follow different physical laws. Such a concept reshapes our idea of what a law of nature truly is. Rather than immutable rules carved into the cosmic fabric, these laws might be emergent behaviors, patterns that arise from deeper, dynamic systems governed by the properties of preons. This aligns with the broader trend in modern physics toward viewing the universe as a complex, adaptive system, not a static machine. As we push forward, collaboration between disciplines will be crucial. Particle physicists, astronomers, cosmologists, and quantum theorists must join forces to unravel this mystery. Each piece of data, whether from a high-energy collision, a deep space telescope, or a computer simulation, could be the key to unlocking the next era of scientific discovery. This makes astrophysical observations a crucial parallel path to the collider-based approach. Telescopes and detectors capable of observing gravitational waves, neutrinos, and electromagnetic spectra across the range, radio, infrared, visible, ultraviolet, X-ray, and gamma-ray, could one day catch a glimpse of an object behaving in ways that defy the expectations of neutron stars or black holes. For example, a compact object with greater density than a neutron star, but lacking the event horizon characteristic of a black hole, might point directly to a Preon star. Such a discovery would not only shake the foundations of astrophysics but also offer the first indirect evidence that preons are real. In recent years, the rapid advancement in observational technologies has given scientists new tools to hunt for these elusive objects. Instruments like the Event Horizon Telescope, LIGO and Virgo observatories, and the upcoming James Webb Space Telescope all provide different windows into the high-energy and high-gravity universe. The detection of unexpected mass-to-radius ratios in compact stars, or the observation of gravitational wave signatures from mergers that do not match any known pattern, could all hint at the presence of a new class of matter, preonic matter. One particularly promising avenue is the study of pulsars. These rapidly spinning neutron stars emit beams of electromagnetic radiation from their magnetic poles. Any variation in their spin-down rates, pulse timing, or gravitational interactions with nearby bodies could reveal deviations from what is expected of ordinary neutron star physics. Some models predict that Preon stars might mimic pulsar behavior but exhibit subtleties in their signals, such as anomalously high mass, unusually strong magnetic fields, or bizarre rotational dynamics. Theoretical astrophysicists have begun crafting simulations of what a Preon star might look like, how it would form, and how it would evolve over time. These models are crucial for giving observational astronomers something to compare their data against. Without theoretical predictions, it becomes nearly impossible to identify a novel object, since so many stellar remnants can appear similar in observational data. A Preon star might only reveal itself through a subtle mismatch between predicted neutron star properties and actual measurements, perhaps an object that is just a bit too massive, a bit too small, or radiating in an unexpected spectrum. Beyond the physical signatures, there are thermodynamic and quantum mechanical clues to watch for. Preon matter, being fundamentally different in composition and internal interactions, would behave differently under extreme conditions. For example, the cooling rate of a Preon star could be much faster or slower than a neutron star due to differences in heat capacity and emission mechanisms. Similarly, the star's response to tidal forces during a close binary orbit could deviate significantly from anything seen in known stellar remnants. These differences, though subtle, can accumulate into patterns that betray the presence of something wholly unfamiliar. To model what Preon stars might look like, how they would evolve, and what observational signatures they might produce, theoretical astrophysicists have begun creating increasingly complex simulations. These simulations incorporate hypothetical equations of state tailored for preonic matter, formulations that attempt to describe how pressure and density interact at energies far beyond those found in neutron stars. Unlike neutron stars, which are stabilized by neutron degeneracy pressure, Preon stars would rely on Preon degeneracy pressure, a force that remains purely theoretical but could represent a new kind of stability at the smallest scales of matter. These models often require input from quantum chromodynamics, QCD, and extensions of the Standard Model, including supersymmetry, technicolor theories, or other exotic frameworks. The results of such models vary widely, as so much of the behavior of preonic matter remains speculative. Some predict that Preon stars could be only a few kilometers in diameter but weigh several solar masses. Others suggest that Preon stars might be more compact than any known object except black holes, existing just shy of forming an event horizon. Despite their incredible density, Preon stars might not emit light in the traditional sense. Unlike normal stars, they don't undergo fusion, and unlike neutron stars, they may lack the residual heat that causes thermal X-ray emission. Instead, their presence could be inferred from their gravitational interactions, bending light from background stars, perturbing nearby bodies, or generating gravitational waves when they collide or spiral into black holes. These indirect detection methods mirror how exoplanets were discovered before being seen directly. Gravitational lensing provides one of the most promising avenues for detection. If a Preon star were to pass in front of a more distant star, it could bend the light in subtle but detectable ways. Unlike a black hole, it wouldn't produce a full shadow or accretion disk. Instead, its mass and density could distort the starlight in a unique pattern, potentially revealing the object's presence. This kind of lensing, especially when observed across multiple wavelengths, could help distinguish a Preon star from other massive objects. Another avenue lies in the search for unexplained mass in binary systems. There are known stellar pairs where one component is invisible yet exerts a significant gravitational force. While many of these are explained by black holes or neutron stars, some exhibit anomalies in timing or motion that resist easy classification. If such a companion star has a mass too great for a neutron star but shows no signs of an event horizon, it could point to the presence of a Preon star. One of the most tantalizing implications of Preon stars is their potential to redefine the concept of compactness. In astrophysics, compactness is a measure of how much mass is squeezed into a given volume. Preon stars, if they exist, would push this measure to the absolute extreme. Such an object would be a kind of cosmic paradox, denser than a neutron star but not a black hole. It would challenge the known limits of gravitational collapse and force physicists to reconsider the thresholds at which spacetime itself begins to warp. There's also the potential link between Preon stars and the mysterious phenomena of fast radio bursts, FRBs. These are extremely short, bright pulses of radio waves that originate from deep space, lasting only milliseconds but releasing more energy in that time than the sun does in days. While some FRBs have been traced to magnetars, highly magnetized neutron stars, others remain unexplained. Some theorists have speculated that collisions involving Preon stars, or even internal quakes within them due to exotic phase transitions, could generate such intense bursts of radiation. Even more speculative is the idea that Preon stars might not be stable at all. Depending on the properties of preons and their binding energies, such stars might exist only transiently, perhaps as intermediate states during the collapse of more massive stars or the early moments of the Big Bang. If so, they could have formed in the primordial universe, leaving behind subtle imprints in the cosmic microwave background or contributing to the spectrum of high-energy cosmic rays we detect today. Another compelling avenue for exploration is whether Preon stars could have played a role in dark matter. If these objects formed shortly after the Big Bang and are numerous enough, they might contribute significantly to the mass of galaxies without emitting light. Unlike black holes, they wouldn't generate detectable Hawking radiation, and unlike neutron stars, they wouldn't be hot or magnetically active. Their invisibility combined with mass would make them ideal dark matter candidates, massive, undetectable, and gravitationally influential. This leads to the exciting possibility that dark matter isn't some exotic particle but a population of ultra-dense preonic objects scattered across the cosmos. These could exist in halos around galaxies, affect the rotation curves of spiral arms, and influence large-scale structure formation. Although speculative, the Preon star hypothesis might kill two cosmic birds with one stone, explaining both the substructure of matter and the missing mass of the universe. However, caution is essential. As seductive as these ideas are, they remain, for now, firmly in the realm of theoretical speculation. No Preon has been detected, no Preon star observed, and the models themselves rely on untested extensions of known physics. But science progresses by asking daring questions and testing them with rigor. What makes the study of Preon stars compelling is that it operates at the bleeding edge of both particle physics and cosmology, inviting us to connect the unimaginably small with the incomprehensibly vast. The pursuit of Preon stars isn't just about discovering new types of matter, it's about understanding the deep architecture of reality itself. If such objects do exist, they would redefine our notions of mass, density, and the very nature of space-time. They would expand the frontier of human knowledge into territories once reserved for imagination alone. And perhaps, just perhaps, they would give us a glimpse into the foundational blueprint from which the cosmos was built. Gravitational lensing provides one of the most promising avenues for detection. If a massive object like a Preon star were to pass in front of a distant light source, its intense gravity would bend the light in a measurable way. This effect, known as gravitational microlensing, has already helped astronomers detect black holes and exoplanets. A Preon star, due to its extreme compactness and density, would produce a distinctive lensing signature, short-lived, sharp, and differing in duration and intensity from other known compact objects. Anomalous microlensing events could therefore become one of the most tantalizing hints that Preon stars are more than theoretical constructs. In addition to microlensing, Preon stars could also be identified through their role in binary systems. If such an object existed in orbit with a more conventional star, its immense gravitational pull would alter the orbital dynamics in detectable ways. The timing of eclipses, Doppler shifts in spectral lines, and variations in the pulsation of the companion star could all betray the hidden presence of a compact and invisible mass. If the inferred mass exceeds what is physically allowable for a neutron star but lacks the telltale signs of a black hole, it could point to the existence of a new category altogether. Another possibility arises from their potential involvement in gravitational wave events. The advent of gravitational wave astronomy has allowed scientists to listen to the universe in ways never before possible. The ripples in space-time produced by massive collisions can carry unique information about the objects involved. If two Preon stars were to merge, or if a Preon star were to collide with a neutron star or black hole, the resulting waveform might differ subtly from known mergers. These deviations, though minute, could be captured and analyzed, providing indirect evidence of Preon matter. Moreover, Preon stars may emit bursts of high-energy particles or radiation during such catastrophic events. Gamma-ray bursts, for instance, are some of the most energetic explosions in the universe, and while many are attributed to neutron star mergers or supernovae, some events defy conventional explanations. The collapse of a Preon star or the sudden transition of a neutron star into a Preon star might release energy in unusual ways, possibly accounting for some of the more mysterious or unclassified gamma-ray bursts already observed. From a cosmological perspective, Preon stars could have formed in the early universe, just moments after the Big Bang. During this epoch, the universe was dense, hot, and chaotic, conditions theoretically conducive to the creation of stable or metastable preonic matter. If true, then some Preon stars might be primordial relics, older than galaxies, silently wandering the cosmos. Their survival across billions of years would offer a rare glimpse into the physics of the universe's first seconds, and their detection could help refine our understanding of cosmic evolution. Some speculative theories go even further, suggesting that Preon stars might contribute to the mysterious dark matter that makes up roughly 27% of the universe. Dark matter, as it stands, does not interact electromagnetically, making it invisible to all forms of light. It reveals itself only through gravity, and Preon stars, if they are both massive and dark, could fit this description. While this would not account for all dark matter, even a partial contribution would be revolutionary. There's also a fascinating possibility that Preon stars are not only extremely rare but incredibly common, hidden among the vast catalog of unidentified or misclassified compact objects. Some astrophysical anomalies, such as stars with unexpectedly high masses or unexplained gravitational signatures, might, in fact, be misunderstood Preon stars. If so, they may already be lurking in our observational data, awaiting discovery by more refined analysis or future technologies. The search for Preon stars isn't just about detecting a new kind of stellar object, it's also a doorway into an entirely new layer of physics. If preons exist, they would necessitate a radical revision of the Standard Model, possibly unifying quarks and leptons under a more fundamental framework. This would have far-reaching implications, from particle physics to cosmology, potentially explaining phenomena like neutrino masses, dark energy, or the matter-antimatter asymmetry in the universe. One of the reasons Preon theories remain on the fringe is the absence of experimental evidence. No particle collider has yet produced any signs of subquark constituents, and no astrophysical observation has definitively pointed to a Preon object. Still, many of the biggest discoveries in science began as wild speculation. Black holes, for instance, were once considered mathematical curiosities, not physical entities. It took decades of indirect evidence before their existence was accepted, and even longer before they were directly imaged. Theoretical models continue to evolve, incorporating the latest findings from both astrophysics and quantum theory. Some researchers are exploring whether Preon stars might exist in a metastable state, lasting for billions of years but eventually decaying into more conventional matter or collapsing into black holes. Others are investigating whether preonic matter could have unusual interactions with dark matter or whether it might produce novel particles that could be detected in future experiments. Ultimately, the quest to discover or rule out Preon stars is a testament to the human desire to peel back the layers of the universe. From the atoms we touch to the stars we see, every structure appears to be made of smaller parts. If quarks are not the end of the road, then preons may be the next step, a deeper understanding of the architecture of matter, energy, and existence itself. If detected, such anomalies would compel scientists to rethink their understanding of stellar evolution, gravitational physics, and the limits of matter. They could point to a form of matter more fundamental than quarks and open a new chapter in the study of cosmic evolution. Preon stars would force a re-evaluation of the end stages of stellar life and the role ultracompact objects might play in the architecture of the universe. Instead of ending as black holes or neutron stars, some stars might compress even further into preon configurations under the right conditions, adding complexity to the simplistic binary outcome of stellar death we currently teach. Preon stars could also help solve long-standing cosmological mysteries. One of the most intriguing is the problem of dark matter. While numerous particles have been proposed to account for dark matter, ranging from WIMPs, weakly interacting massive particles, to axions, none have been conclusively identified. If Preon stars exist in abundance throughout the universe, particularly in galactic halos where dark matter is believed to reside, they might account for a portion of the gravitational mass currently attributed to dark matter. Their lack of electromagnetic interaction would make them effectively invisible, while their immense gravitational influence would match the effects astronomers have been trying to explain for decades. The idea of macroscopic dark matter, which includes massive compact halo objects, machos, has fallen out of favor compared to particle dark matter theories, largely due to a lack of observational support. However, the unique lensing characteristics and orbital dynamics introduced by Preon stars might revive interest in this area. If machos made of preonic matter do exist, they could constitute a hidden component of dark matter that has gone unnoticed simply because we weren't looking for the right signs. Another area of interest lies in the role Preon stars could have played during the early universe. Shortly after the Big Bang, conditions were unimaginably hot and dense, ideal for the formation of exotic matter. In such a turbulent epoch, it's plausible that pockets of matter collapsed directly into Preon stars before the universe expanded and cooled. These primordial Preon stars, if they exist, might still be out there, acting as silent relics from the earliest moments of time. Their discovery would not only confirm a new state of matter but also provide a glimpse into conditions that existed just microseconds after creation itself. Theoretically, Preon stars could also act as natural laboratories for testing physics beyond the standard model. Because they would operate under conditions of extreme energy and density, they might exhibit behaviors governed by forces or particles not accounted for in current theories. Observing these behaviors, either directly or indirectly, could shed light on new fundamental forces, symmetry breakings, or hidden dimensions. In this way, Preon stars wouldn't just be astrophysical curiosities. They would be keys to unlocking the deepest truths about reality. Further speculation suggests that Preon stars might possess unusual surface or crust properties. If composed entirely of preonic matter, their surfaces could be smoother, denser, or even more reflective than those of neutron stars. Alternatively, some models predict a thin outer layer of quark, or neutron matter that envelopes a preonic core. This hybrid structure might give rise to strange electromagnetic emissions, exotic seismic activity, or unanticipated responses to tidal forces, any of which could serve as indirect signatures of their presence. The magnetic fields of Preon stars are another area ripe for exploration. Neutron stars, especially magnet-stars, are known for possessing some of the strongest magnetic fields in the universe. A Preon star, due to its even greater density and rotational energy, might generate magnetic fields of even higher magnitude. These could influence surrounding plasma in novel ways, disrupt the orbits of nearby bodies, or even create beams of radiation unlike any known pulsar. Unusual radio signals or bursts of energy might one day be traced back to these hypothetical engines of magnetism. Another intriguing idea is the potential for Preon stars to collapse into black holes. Since Preon matter is so dense, there's a threshold beyond which not even preonic degeneracy pressure could prevent gravitational collapse. This would create black holes of comparatively small mass but extraordinary compactness in their prior state. If such a collapse occurred, the resulting gamma-ray burst or gravitational wave could carry a unique fingerprint of the transition from a Preon star to a singularity, adding another clue to the observational trail scientists are eager to follow. The collapse of a Preon star might also produce new kinds of high-energy particles. As the preonic matter is crushed past its limit, it could release exotic particles or radiation bursts never before seen. Instruments designed to capture cosmic rays, neutrinos, or gamma rays might one day detect these events, prompting questions about their origin and leading back to the theoretical framework surrounding Preon stars. If these events could be correlated with specific areas in the sky, or with known gravitational disturbances, the case for Preon stars would grow stronger. Despite all this theoretical richness, one of the greatest challenges remains observational confirmation. Telescopes, detectors, and satellites today are only beginning to scratch the surface of what might be detectable in the ultra-dense universe. As technology improves and data from missions like the James Webb Space Telescope, LISA, Laser Interferometer Space Antenna, and the Square Kilometer Array pour in, we may find the first indirect signs of Preon stars hiding among the noise. It will take careful analysis, machine learning algorithms, and new ways of thinking to isolate their potential signatures. The search for Preon stars also highlights a broader philosophical point about science. Much of what we discover begins not with observation but with imagination. Theorists extend known laws into unknown territories, and only then do observational astronomers attempt to catch up. Preon stars, while unconfirmed, are a natural evolution of this process, hypotheses born at the intersection of particle physics, astrophysics, and cosmology. They demonstrate the power of speculative science grounded in logical extrapolation, even if the road to empirical evidence is long and uncertain. As we expand our capabilities and refine our tools, the potential discovery of Preon stars could radically transform our understanding of the cosmos. They would represent not only a new type of celestial object but also a new state of matter, one that bridges the gap between the subatomic world and the astronomical. They would also hint at hidden aspects of nature still waiting to be uncovered, whispering from the darkest, most compact corners of the universe. Preon stars, if confirmed, could constitute a hidden component of the dark matter equation that has been overlooked due to their elusive nature. Their tiny size and lack of electromagnetic radiation make them nearly impossible to detect with conventional telescopes, but their gravitational signatures, subtle warps in starlight, distortions in stellar orbits, and contributions to galactic mass, might be enough to uncover their presence if analyzed with sufficient precision. If confirmed, this would revolutionize not only dark matter research, but also how we think about the fundamental makeup of the cosmos. The role of Preon stars in cosmic evolution could extend even further. During the earliest moments of the universe, fractions of a second after the Big Bang, conditions may have favored the formation of ultra-dense objects long before stars or galaxies took shape. These so-called primordial Preon stars might still exist today, scattered throughout the intergalactic void or hidden in galactic halos, forming a relic population of ancient, nearly undetectable mass. If they formed prior to the era of nucleosynthesis, They could also help explain certain irregularities in the cosmic microwave background or primordial element ratios observed in the early universe. One particularly compelling idea is that these primordial Preon stars could act as seeds for early galaxy formation. In current cosmological models, dark matter halos serve as gravitational wells around which ordinary matter gathers, eventually forming galaxies. If Preon stars existed as dense, gravitationally potent objects in the early universe, they could have played a similar role, helping to gather gas and dust into denser regions and catalyzing the formation of structure far earlier than expected. This hypothesis could offer new insights into why some galaxies appear to have formed surprisingly early in cosmic history. There's also the possibility that Preon stars could be responsible for certain unidentified astrophysical phenomena. Fast radio bursts, FRBs, for instance, are millisecond-long flashes of radio waves that have puzzled astronomers since their discovery. Their origins remain unknown, and while several models have been proposed, including neutron star collisions, magnetar flares, and black hole interactions, none have provided a universally accepted explanation. A speculative but fascinating idea is that collisions or surface instabilities involving Preon stars could produce exotic forms of electromagnetic radiation, including rapid bursts of high-energy radio waves. Other phenomena, like ultra-high-energy cosmic rays, also lack a definitive source. These particles arrive at Earth with energies far beyond what conventional astrophysical processes can easily explain. Preon stars, due to their extreme internal pressures and gravitational dynamics, might be capable of accelerating particles to such velocities, especially if their dense magnetic fields or surface tension properties create unique environments for particle ejection. The internal physics of Preon stars, still entirely theoretical, could harbor unknown mechanisms for generating and releasing such extreme energies. In the realm of high-energy astrophysics, Preon stars might also be implicated in gamma-ray bursts, GRBs. These incredibly powerful explosions are thought to be linked to neutron star mergers or supernovae. But there are outliers, bursts whose energy signatures or durations defy existing models. If a Preon star were to collapse, destabilize, or collide with another compact object, it could release vast quantities of energy in a very short period of time. These events could masquerade as gamma-ray bursts but exhibit atypical temporal profiles, leading to confusion about their origins unless we have the proper theoretical framework in place. Even the life cycle of black holes might be affected by the existence of Preon stars. Currently, black holes are considered to be the ultimate end state of gravitational collapse, with matter compressed into a singularity where known physics breaks down. But if Preon matter represents a lower energy, more stable state of compression, it's possible that some objects thought to be black holes are in fact ultra-compact Preon stars whose event horizons never formed. These so-called black hole mimickers could explain observations that seem to contradict what we expect from traditional black holes, such as unusual gravitational wave echoes or energy emissions that defy general relativity's predictions. In theoretical physics, the notion of a maximum compactness limit is still debated. While general relativity places certain limits on how compact an object can be before it must become a black hole, quantum gravity theories suggest possible exceptions. Preon stars could be examples of such exceptions, objects so dense they flirt with the limits of collapse but are held together by quantum mechanical forces or exotic equations of state. In this sense, they wouldn't just be new astronomical objects, they would be living tests of our most ambitious and incomplete theories about the universe. On a more speculative note, Preon stars could challenge the standard model of particle physics itself. If preons are real, it means that quarks and leptons, the indivisible particles of the standard model, are actually composed of something smaller. This would usher in an entirely new layer of physical law, perhaps governed by forces and interactions that lie beyond the standard model. The detection of a single Preon star might offer stronger evidence for a more fundamental theory than even the discovery of the Higgs boson did for the standard model. Moreover, Preon theory could unify some of the deepest mysteries in physics. One enduring problem is the apparent hierarchy of forces, the huge difference in strength between gravity and other fundamental forces. Some physicists speculate that this might arise because we're not seeing the full picture, perhaps new interactions, confined to the Preon level, provide the missing context. Preon stars, by existing at such an extreme end of physical conditions, might naturally exhibit these hidden dynamics and offer an observational window into their behavior. In the broader philosophical landscape, the existence of Preon stars raises questions about simplicity and complexity in the universe. For centuries, scientists have searched for ever smaller building blocks, from atoms to electrons to quarks. The Preon concept challenges our assumptions about where this hierarchy ends. If nature indeed hides another layer beneath the standard model, then our conception of fundamental needs to evolve. Preon stars would be the macroscopic manifestations of this microscopic truth, a powerful reminder that complexity does not only increase upward but can also deepen inward. Understanding Preon stars also forces us to grapple with the concept of observational limitations. Much of the universe remains hidden not because it's rare, but because it's subtle or obscured by the limits of our instruments. Preon stars, if they exist, might be common and important, yet virtually invisible. This parallels historical scientific shifts where entire classes of phenomena, like microbes or radio waves, remained unknown until technology advanced. The pursuit of Preon stars could therefore be the next chapter in humanity's ever-expanding sensory reach, transforming not only what we see, but what we think is possible. Beyond galactic evolution, Preon stars could have profound implications for our understanding of black holes. Traditionally, black holes are thought to form when the core of a massive star collapses beyond the neutron degeneracy limit, creating a singularity wrapped in an event horizon. However, if Preon stars can exist at densities greater than that of neutron stars but still below the threshold required to form a black hole, they might offer an alternative outcome to core collapse. This could help explain certain cosmic phenomena that resemble black holes in some ways but deviate in others, such as objects with high mass and gravitational pull but lacking the predicted event horizon characteristics. Such an idea introduces the possibility of black hole imposters, or objects that exhibit some black hole-like behaviors, like extreme compactness and gravitational lensing, without actually being black holes. This would have vast consequences for observational astrophysics. Many of the objects currently catalogued as black holes might, in fact, be Preon stars or similar exotic ultradense bodies. It would also mean that the threshold of collapse into a singularity is not as universal as currently believed, suggesting a more nuanced hierarchy of stellar remnants that includes white dwarfs, neutron stars, Preon stars, and finally black holes. This hypothetical sequence would redefine the concept of degeneracy pressure, the quantum mechanical force resisting gravitational collapse. We already understand electron degeneracy pressure in white dwarfs and neutron degeneracy pressure in neutron stars. Preon stars would necessitate an entirely new type of degeneracy pressure based on preonic interactions, perhaps governed by even more fundamental principles of physics than those currently in the standard model. Studying such interactions would provide a window into a new domain of quantum field theory and might unify our understanding of matter at the most elementary level. Moreover, Preon stars could help resolve the information paradox associated with black holes. According to current models, any information that falls into a black hole is lost to the universe, violating principles of quantum mechanics that insist information must be conserved. If some objects thought to be black holes are actually Preon stars, then the issue of information loss might be less pervasive than expected. These stars, though incredibly dense, would not possess an event horizon, allowing information to remain, in theory, recoverable or at least observable in some form. Another area where Preon stars could shake foundational science is in high-energy astrophysics. Pulsars and magnetars, highly magnetized neutron stars, emit beams of electromagnetic radiation with incredible regularity and power. Some of their observed behaviors remain difficult to explain using conventional neutron star models. Preon stars, due to their extreme density and potentially different magnetic field dynamics, might account for some of these anomalies. Their interaction with surrounding spacetime could create novel forms of particle acceleration or radiation that provide fresh insight into gamma-ray bursts, fast radio bursts, and other enigmatic cosmic events. Even more fascinating is the possibility that Preon stars could support entirely new forms of exotic matter or energy interactions. Because of their ultra-dense state, the behavior of particles within them could differ significantly from that in known environments. These conditions might allow physicists to observe phenomena like color superconductivity, or new types of quantum chromodynamics (QCD) phase transitions that occur only under the most extreme densities. This would not only enhance our understanding of fundamental forces but might also lead to practical discoveries in condensed matter physics or quantum computing. From a theoretical perspective, the existence of Preon stars supports the notion that matter is built from successively smaller constituents. Just as the atom was once thought to be the smallest unit until the discovery of protons and neutrons, and later quarks, the proposal of preons continues this tradition of scientific refinement. If we assume that all matter is fundamentally structured, then preons may not be the end of the line either, simply the next rung on an infinite ladder of substructure. Preon stars, as macroscopic manifestations of this idea, would be natural laboratories for exploring these deeper levels of reality. Furthermore, Preon stars might challenge the validity or limits of general relativity. Einstein's equations describe the curvature of spacetime extremely well on large scales, but they begin to break down at quantum scales and near singularities. Preon stars would exist in a regime where quantum effects and gravitational forces are both dominant, offering an ideal testbed for theories attempting to unify general relativity with quantum mechanics. Whether through string theory, loop quantum gravity, or some yet undiscovered framework, understanding Preon stars could be the bridge between the macrocosmic and microcosmic laws of nature. The consequences would also ripple through cosmological models. The early universe's behavior, structure formation, inflationary dynamics, and even the fate of the cosmos might be influenced by the presence of preonic matter. If Preon stars existed from the very beginning, their gravitational influence could have shaped the distribution of matter, the propagation of light, and the evolution of temperature and density across the observable universe. Including them in cosmological simulations might yield better matches to observed data, improving the accuracy of models for dark energy, cosmic acceleration, and galaxy clustering. On a more speculative note, Preon stars might even hold the key to advanced energy sources. Their incredible density implies vast stores of potential energy, locked in the interactions between fundamental particles. If harnessed, however unlikely that may seem with current technology, they could offer a source of energy orders of magnitude beyond anything we presently use. In this sense, Preon stars might play a role in the distant future of civilization, not only as objects of study but also as resources for energy, information, or even transportation through extreme gravitational fields. Philosophically, the existence of Preon stars forces us to confront the limits of human perception and understanding. These objects are beyond the reach of ordinary instruments, and do not emit light in any familiar way. Detecting them requires interpreting indirect clues, minute distortions in gravity, inexplicable radiation signatures, or gravitational wave anomalies. They represent a new frontier, much like black holes once did, challenging us to evolve our instruments, theories, and imagination to keep pace with the hidden architecture of reality. In every direction, cosmology, particle physics, gravitational theory, and astrophysical observation, Preon stars stretch the boundaries of what we think is possible. They promise new insights, new technologies, and perhaps a new understanding of existence itself. And as research continues to push against the edge of the unknown, the question becomes not whether Preon stars exist, but whether we are ready to find them. If Preon stars exist, the interactions between preons, whatever their true nature may be, would define a new class of matter behavior, one that might serve as a bridge between classical and quantum physics, much like how string theory aims to unify all fundamental forces. Unlike the well-studied behaviors of electrons, protons, and neutrons, preon-level interactions remain a mystery. This unexplored regime could be governed by forces or symmetries that have yet to be observed in any particle accelerator or cosmic phenomenon. If these forces are strong enough to support a stable stellar object, they could indicate that our understanding of the universe's building blocks is still in its infancy. From a mathematical standpoint, modeling Preon stars would require the development of new equations of state, relationships between pressure, temperature, volume, and energy density, that apply to this hypothetical matter. The known equations of state for white dwarfs and neutron stars rely heavily on well-understood quantum mechanics. But Preon matter might behave in ways that defy those laws, introducing concepts such as ultra-relativistic degeneracy, higher dimensional pressure gradients, or even exotic topologies within the star's core. These possibilities challenge both numerical simulations and analytical physics, calling for new tools, new languages, and perhaps entirely new branches of theoretical physics. In addition to these physical and theoretical implications, Preon stars could have a profound impact on our philosophical understanding of the universe. They raise questions about what it means to be fundamental. For decades, the search for the ultimate indivisible particle has driven physics forward. First atoms, then protons and neutrons, and now quarks and leptons have taken the spotlight. But if preons exist, and if they form stars, then the current, elementary particles, might just be complex bound states themselves. This would mirror historical cycles in science, where each generation's concept of fundamental matter gives way to a deeper, more intricate understanding. Furthermore, Preon stars might force us to reconsider the life cycle of matter in the cosmos. Traditionally, we think of matter being recycled through stars, from hydrogen fusion to heavier elements, to supernova explosions, to new star formation. But Preon stars, being composed of an entirely different substrate, might not participate in this cosmic recycling. They could represent a dead end in the evolutionary chain of matter, objects that once formed, never change, decay, or contribute further to chemical enrichment. This immutability could mean they are ancient relics of a cosmic era before atoms or elements even existed. Detecting Preon stars poses a monumental challenge, perhaps one of the most difficult in modern astronomy. They would emit little to no electromagnetic radiation, making them effectively invisible to traditional telescopes. However, their immense mass and density would allow them to exert powerful gravitational effects. This means that gravitational lensing, where the Preon star bends the light of more distant objects, could be one way to infer their existence. Microlensing surveys, which look for brief light distortions as objects pass in front of stars, might already contain data that could hint at Preon stars, though such signals would likely be subtle and easily confused with more conventional objects like rogue planets or black holes. Another avenue could involve gravitational wave detection. If two Preon stars were to collide, they would produce ripples in spacetime, much like black hole mergers, but with potentially different frequency signatures. These unique waveforms might stand out against the growing catalog of gravitational wave events. Advanced detectors like LIGO, Virgo, and the upcoming LISA mission could, in theory, detect such anomalies. If gravitational wave signals were found that didn't match known neutron star or black hole profiles, they might point to the existence of a new class of object, Preon stars among them. There's also the possibility that Preon stars are responsible for certain unidentified high-energy cosmic events. Fast radio bursts, FRBs, gamma-ray flashes, and certain types of supernova remnants defy easy classification. Some of these might be explained by the interactions of Preon stars, whether through collisions, collapses, or magnetic field disturbances. Their extreme densities could allow them to store vast amounts of potential energy, released suddenly in violent outbursts when triggered by external forces or internal instability. Magnetism, in fact, could be a key characteristic of Preon stars. Neutron stars are known for their strong magnetic fields, and Preon stars, being even denser, might amplify this feature to unprecedented levels. These hypothetical magnetic monsters could twist spacetime around them and influence the motion of charged particles far beyond their immediate vicinity. If such magnetic signatures could be isolated and identified, it might become one of the most viable observational pathways toward discovering Preon stars. The formation of Preon stars, too, raises profound questions. How exactly could they form in the first place? Would they arise from collapsing neutron stars? Or would their birth have to occur in the ultra-early universe, when conditions were still extreme enough to allow the aggregation of preons? If the latter, it would suggest that these objects are older than any galaxy, any star, and perhaps any structure in the cosmos. They could be the frozen echoes of a time when matter as we know it had not yet come into being, a phase transition of the universe locked away in compact, dark remnants. And what of their internal structure? Unlike stars composed of plasma or neutrons, Preon stars might exhibit unfamiliar internal configurations. They could contain crystalline preon lattices, quark-gluon condensates, or even higher-dimensional cores shaped by forces we do not yet understand. The idea of stable matter existing under pressures trillions of times higher than those inside a neutron star pushes our understanding of solid-state and nuclear physics to its breaking point. Inside these stars, the speed of sound, the curvature of space-time, and the behavior of fundamental forces might all differ from anything we can currently observe or measure. Preon stars also challenge the notion of singularities. In current physics, black holes are considered singularities where density becomes infinite and known laws break down. But if preon matter can exist at greater densities than neutron matter without collapsing into a black hole, then perhaps singularities are not inevitable. Perhaps the universe has mechanisms to avoid these mathematical paradoxes by forming ultradense but finite configurations like preon stars instead. This line of reasoning could open the door to reformulating our understanding of gravity and collapse, moving away from singularities toward a more unified theory that incorporates quantum resistance to infinite densities. The existence of preon stars could also offer insights into the early conditions of the universe. If these objects formed shortly after the Big Bang, they may be relics of a time when the universe was governed by physics vastly different from what we observe today. During the first fractions of a second after the Big Bang, matter may have existed in forms we can't currently replicate in laboratories. Preon stars, if they emerged in this epoch, would serve as cosmic fossils, frozen records of the universe's earliest and most extreme states. Understanding them might help decode the events of cosmic inflation or provide clues about what happened before the quark-gluon plasma era. Their formation would require conditions of immense density and temperature, possibly exceeding those in supernova cores. If so, it raises questions about the mechanisms behind such formation. Could preon stars be born directly from primordial fluctuations? Might they have condensed from high-density regions during the Big Bang itself, bypassing the stages of baryonic matter entirely? Or could they have formed later, during the death of exotic stars composed of matter denser than anything currently known? These formation scenarios would reshape how we understand stellar evolution, black hole thresholds, and the overall mass distribution in the cosmos. Moreover, preon stars might offer a compelling explanation for the abundance of unexplained compact objects observed throughout the universe. In various surveys, astronomers have found stellar remnants whose masses and sizes don't align neatly with current models of white dwarfs, neutron stars, or black holes. Some of these might be unusually dense neutron stars, but others remain completely enigmatic. Preon stars, with their ultra-compact profiles and high gravitational influence, could fill this observational gap. If confirmed, they would not only account for these anomalies but also expand our stellar taxonomy in a revolutionary way. Another fascinating angle is how preon stars might interact with their surroundings. Because of their immense gravity and possible small size, they could serve as cosmic vacuum cleaners, pulling in matter silently and invisibly. Unlike black holes, which leave telltale signs like accretion disks and X-ray emissions, preon stars might absorb material with fewer detectable byproducts. This would make them much harder to spot, possibly contributing to the universe's missing mass problem and adding to the mystery of dark matter. Their stealthy nature could explain why they've eluded detection despite potentially existing in significant numbers. One way scientists could detect these elusive objects is through gravitational lensing. When a massive object passes in front of a distant star or galaxy, its gravity bends the light, magnifying and distorting the background source. This effect, known as microlensing, has already been used to detect black holes and exoplanets. If preon stars exist, they too could act as gravitational lenses. The challenge would be distinguishing their lensing signatures from those of other compact objects. However, their incredibly high density might produce subtle anomalies and light-bending patterns that, with advanced enough instruments, could serve as their fingerprints. In the realm of gravitational waves, Preon stars also present exciting possibilities. The merger of two Preon stars, or a Preon star and a neutron star, could produce a distinct gravitational wave signature unlike anything currently in our catalogs. These waves would differ in frequency, duration, and amplitude, potentially giving scientists a new category of waveforms to search for. As gravitational wave observatories like LIGO and Virgo become more sensitive, and as next-generation detectors like LISA come online, we may soon have the capability to identify these unique signals and match them to exotic phenomena like Preon star collisions. Furthermore, Preon stars could alter the landscape of nuclear astrophysics. Our understanding of nucleosynthesis, the process by which elements are forged in stars, relies on the behavior of neutrons and protons under extreme conditions. If Preon stars are real, they may influence or disrupt nucleosynthesis processes in supernovae or neutron star mergers. The presence of ultradense Preon matter could either absorb surrounding material or catalyze reactions not currently accounted for, possibly explaining discrepancies in observed elemental abundances across the universe. Even more intriguingly, Preon stars might play a role in the ultimate fate of matter. In scenarios of long-term cosmic evolution, where black holes slowly evaporate via Hawking radiation and stars burn out into white dwarfs and neutron stars, Preon stars could represent an enduring class of matter. If they are stable and immune to further collapse, they could survive for trillions of years, perhaps longer than any other structure in the cosmos. In such a future, the universe might eventually be populated by nothing more than cold photons, neutrinos, and these tiny ultradense relics of a bygone, energetic age. The thermodynamics of Preon stars also invite deep exploration. Given their density, their internal temperatures and energy distributions could be wildly different from traditional stars. If they exhibit superconductivity, superfluidity, or other quantum states en masse, they might represent the largest manifestations of quantum phenomena in the universe. This would make them not only astrophysical objects but also natural laboratories for condensed matter physics at scales no human-made experiment could match. And then there's the question of whether Preon stars could evolve or transform over time. Could they accrete enough matter to tip into black hole status? Might they decay, shedding preons in rare processes over eons? Or could they even give rise to entirely new forms of matter, unknown and unimaginable, as their internal pressures and energies push into previously unexplored realms? These questions blur the line between astrophysics and speculative cosmology, making Preon stars a gateway to some of the universe's most profound mysteries. Preon stars might even intersect with the search for extraterrestrial intelligence. Some have proposed that highly advanced civilizations might use ultradense stars as energy sources or computational substrates. The immense density and gravitational potential of Preon stars could, in theory, support megastructures or extreme physical conditions required for certain types of exotic technology. While highly speculative, it adds a layer of intrigue. Could Preon stars not only be natural wonders but also engineered remnants or tools of cosmic intelligences far beyond our comprehension? The concept of Preon stars reminds us of the boundless frontier that still exists in astrophysics. Despite all the satellites, telescopes, and theories we've developed, the cosmos continues to hint at deeper layers of complexity. Preon stars, if real, would fundamentally reshape our understanding of mass, structure, and the nature of matter itself. Their study would demand new instruments, new theories, and perhaps new ways of thinking. But as with all great scientific revolutions, the journey begins with a question, and Preon stars may be one of the most important questions we have yet to answer. Preon stars, with their ultra-compact profiles and high gravitational influence, could be masquerading as black holes or exotic neutron stars. Their gravitational signature might be nearly identical to those of smaller black holes, making them extremely difficult to distinguish with current observational tools. However, with the development of more sensitive gravitational wave detectors and advanced X-ray observatories, scientists might eventually identify unique fingerprints, subtle anomalies in the timing, frequency, or decay of signals that point to something other than known objects. These distinctions could become one of the most exciting frontiers in astrophysical observation. For example, the gravitational waves emitted during the merger of two Preon stars, or even a Preon star with a neutron star, could differ significantly from those produced by black hole mergers. The waveform might show an unexpected chirp or cutoff, or display an energy profile inconsistent with known stellar models. If researchers detect such signatures, it could lead to a revolutionary shift in our cataloging of cosmic events, perhaps even identifying entire new classes of stellar remnants previously hidden in plain sight. Likewise, electromagnetic observations might help. If a Preon star accretes matter, as some neutron stars and black holes do, it could emit radiation patterns that deviate from expectations. The energy output might be more stable, less chaotic, or reach different frequencies than traditional accretion models predict. Furthermore, its surface, or what passes for a surface in such an object, could reflect or emit particles in ways that challenge conventional thermodynamics or radiation laws. Spectral anomalies in X-ray or gamma-ray readings might offer the first visual clues to these mysterious entities. There's also the tantalizing possibility that Preon stars might interact differently with dark matter. If preons are affected by unknown forces or exist partially in higher dimensions, they might serve as attractors or repellers of dark matter particles. This could cause Preon stars to develop unique halos of exotic matter, observable through gravitational lensing or subtle shifts in light paths around them. Detecting such phenomena could provide a bridge between two of the most perplexing concepts in modern astrophysics: the nature of dark matter and the possibility of subquark structures. Their potential role in cosmic evolution is another exciting avenue. Preon stars, depending on how often they form and how long they last, might have influenced galaxy formation, altered early gravitational wells, or even disrupted the growth of black holes. If they are exceptionally stable, they could persist for billions of years, scattered across the universe as silent observers of galactic history. Alternatively, if they're unstable, they may decay in exotic ways, perhaps emitting bursts of unknown radiation or collapsing into black holes with a violent release of exotic particles. The existence of such objects could also reshape our thinking about the ultimate fate of matter. If preons are the endpoint of all collapse, then black holes may not be the final frontier. Instead, some collapsing stars might halt just before reaching singularity, held in balance by a new kind of degeneracy pressure stemming from preon interactions. This would replace the traditional narrative of inescapable collapse with a more nuanced story, where some matter remains forever locked in these dense, nearly invisible configurations. This idea could also affect how we interpret black hole evaporation. Hawking radiation, the quantum process by which black holes slowly lose mass, may interact differently if the black hole core isn't a true singularity but instead a Preon star. Perhaps the evaporation stops, or releases particles unlike any we've catalogued. If this turns out to be true, Preon stars might help explain how information is preserved through black hole evolution, a central mystery in the field of quantum gravity. Furthermore, the study of Preon stars would demand a reevaluation of fundamental constants and assumptions. The speed of light, Planck's constant, and other core values may behave differently under extreme Preon-level conditions. Tiny variations or localized effects could manifest in these stars, subtly bending known laws of physics. Such findings might not only revise existing models but inspire entirely new ones, integrating preons into a grand unified theory that connects all forces and particles in a cohesive framework. In the realm of computational astrophysics, simulating Preon stars poses both a monumental challenge and an opportunity. Current supercomputers are barely able to model neutron star collisions or black hole dynamics. Introducing preons, particles with uncertain properties and behaviors, would require revolutionary advances in algorithm design, quantum simulation, and data processing. Yet the rewards of success would be unprecedented. The ability to virtually build a Preon star, tweak its parameters, and watch its behavior unfold in real time. Public interest in such concepts could also explode once mainstream awareness grows. The notion of stars made of particles smaller than anything we know has a poetic appeal, blending mystery with cutting-edge science. It taps into humanity's enduring curiosity about the ultimate nature of existence. With thoughtful storytelling and compelling visuals, Preon Stars could inspire a new generation of physicists, astronomers, and dreamers, people eager to pierce the veil of the unknown and reveal what lies beyond the frontier of matter. There's also the tantalizing possibility that Preon Stars might interact with dark matter or dark energy in ways ordinary matter cannot. If preons are more fundamental than quarks and leptons, they may interact with components of the universe that remain completely invisible to us. Imagine if Preon Stars serve as natural dark matter detectors, not through conventional collisions or decay products, but by subtly warping the gravitational field around them in patterns that align with dark matter distributions. If such a correlation were discovered, it would be a monumental breakthrough in both particle physics and cosmology. These hypothetical interactions open new doors to understanding dark matter itself. Perhaps dark matter is composed of a different configuration of preons, particles that are invisible to standard detection methods but gravitate and clump under the right conditions. If this is true, then Preon Stars might be partially composed of dark matter or might even originate in regions of space where dark matter density is particularly high. This could explain the mysterious behaviors of some gravitational lensing events, or the unexpected rotation curves in galaxies. Even more compelling is the possibility that Preon Stars play a role in cosmic structure formation. During the early stages of the universe, the presence of ultra-dense objects could have acted as seeds around which matter began to clump. This process might have accelerated galaxy formation or contributed to the distribution of voids and filaments on the grandest scales. Preon Stars, if they existed in sufficient numbers, could subtly influence the layout of the universe itself, woven into the very fabric of its cosmic architecture. And then there's the question of longevity. How long could a Preon star persist? Given their density and stability, some models suggest they could be nearly eternal, resisting decay, gravitational collapse, or evaporation. In a universe destined to expand and cool indefinitely, Preon Stars could be among the final remnants of structure, surviving long after stars, galaxies, and even black holes have faded. They might be the monuments left behind at the heat death of the universe, silent, cold, and incomprehensibly dense. Their lifespans could stretch far beyond the current age of the universe. If black holes evaporate via Hawking radiation over quadrillions of years, what becomes of Preon Stars? If they are more stable, they may eventually become the last source of gravitational energy in an otherwise inert cosmos. This endurance would make them cosmic time capsules, preserving information and matter longer than any other known object. The implications for information storage are equally fascinating. Given their high density and the possibility of unique quantum properties, Preon Stars might be capable of containing immense amounts of information. Some theorists speculate that such dense matter could preserve complex quantum states far better than any artificial construct. If so, Preon Stars might serve as natural repositories of cosmic data, potentially holding imprints of the conditions that created them. This idea stretches into the realm of metaphysical speculation. Could Preon Stars encode information about the early universe, or even about universes that existed before our own? If they are formed from preons, and if preons represent a more fundamental reality than quarks, then they may tap into aspects of reality that are currently beyond the reach of even our most advanced theories. These possibilities blur the line between science and philosophy and invite a deeper contemplation of what matter and existence really mean. Another aspect that cannot be ignored is the potential hazard Preon Stars might pose. Given their extreme density, even a small one would carry immense gravitational pull. If a Preon star the size of a baseball passed through the solar system, it could wreak havoc, disrupting planetary orbits, pulling apart moons, or slingshotting matter across space. Thankfully, no such object has been observed locally, but the mere theoretical possibility underlines the need for continuous deep space monitoring. Interestingly, the theoretical mass-to-size ratio of Preon stars would render them nearly invisible to current detection methods. Their event horizons, if they have any, would be smaller than a neutron star's but without the light-blocking properties of a black hole. This means that detecting them would require indirect methods, carefully analyzing motion anomalies, gravitational lensing patterns, or perhaps even seismic activity on large planetary bodies caused by close encounters. Theoretical simulations also suggest that Preon stars, due to their density, might not obey classical rules of general relativity in expected ways. Some proposals argue that within their cores, gravity could behave differently, perhaps weakening or exhibiting quantum properties under such extreme conditions. If validated, this could provide a real-world laboratory for testing quantum gravity or the unification of general relativity with quantum mechanics, something physicists have long dreamed of. And there's the human angle, the deep, emotional, existential curiosity that drives us to explore these ideas. Preon stars are not just esoteric equations on a blackboard. They represent the pursuit of the ultimate question: what is matter really? What lies beneath the visible, beneath the known, beneath the assumed foundations of our universe? Every time we peel back a layer, we find new complexity, new wonder, and new mystery. In contemplating Preon stars, we are staring into a mirror that reflects not just the structure of the cosmos, but our own desire to understand what lies beyond the horizon of knowledge. Some models suggest that Preon stars could outlive most other celestial objects in the universe. While ordinary stars burn out, collapse, or explode over millions or billions of years, Preon stars, if they are truly stable configurations of ultra-compressed matter, might endure for eons longer than the current age of the universe. They may be relics from an ancient epoch, potentially formed mere moments after the Big Bang, and still persist today in hidden pockets of the cosmos, silent and undetectable by most current means. If this is true, they could serve as literal fossils of the universe's earliest physical laws. Before quarks, before protons, before atoms, if such an era existed and gave rise to stable Preon-based matter, then Preon stars might preserve in their structure a pristine signature of the physics that governed that epoch. Studying them, or even confirming their existence, could be the equivalent of opening a time capsule sealed when the universe was less than a second old. The implications for both theoretical and experimental physics would be extraordinary. In terms of composition, Preon stars challenge our understanding of matter at every level. The idea that preons can form stable, self-gravitating configurations means that the degeneracy pressure we know from neutron stars, produced by neutrons resisting further compression, would be replaced by a much more exotic pressure. This pressure would stem from the interaction and behavior of preons themselves, perhaps obeying different statistical mechanics, or obeying entirely new physical laws. Some theories propose that these objects might also possess an incredibly small radius compared to their mass. A Preon star the mass of the Earth might be no larger than a marble. Their surface gravity would be so intense that escaping it would be practically impossible, making them virtually invisible without indirect detection methods. This could explain why we haven't seen them yet. Either they're too small to detect, or their signals are buried within the noise of other astrophysical phenomena. But even their invisibility raises questions. What if we have seen them, but didn't recognize them? Some gamma-ray bursts, for instance, might originate not from collapsing neutron stars or black holes, but from Preon star interactions. A collision between two Preon stars could theoretically release enormous amounts of energy in a very short burst, similar to what we currently associate with neutron star mergers. But the energy profile, duration, and spectral composition might offer subtle differences, ripe for reinterpretation. Gravitational lensing provides another possible avenue for detection. If a Preon star passed in front of a distant object, the bending of light it causes might betray its existence. However, because of its extremely compact size, the lensing effect would be brief and incredibly sharp, difficult to detect without continuous, high-resolution sky surveys. If we ever spot such a fast, intense lensing event with no visible source, it might just be a Preon star casting its invisible shadow. In the realm of high-energy astrophysics, there's also speculation that Preon stars could act as ultra-high-energy particle accelerators. If their surface gravity is steep enough, particles escaping, or even being ejected by magnetic fields, could reach energies far beyond anything we can produce on Earth. Cosmic rays that puzzle scientists today might originate from Preon stars flinging particles across the galaxy at unimaginable speeds. There's also the intriguing possibility of Preon stars hosting magnetic fields of absurd strength. Much like magnetars, neutron stars with extreme magnetic fields, Preon stars might amplify this effect due to their density and internal dynamics. Such magnetic fields could distort space itself in localized regions, creating unique distortions in radio signals or potentially interfering with spacecraft navigation systems if one were ever to pass close enough. From a quantum mechanics standpoint, Preon stars could challenge the Heisenberg uncertainty principle as applied to high-density systems. At such compact scales, the positions and momenta of particles might reach limits we haven't yet observed, revealing new aspects of quantum gravity or quantum chromodynamics. The behavior of particles within a Preon star might defy the very equations we use today to define matter. Another avenue of exploration is entropy. Conventional black holes have incredibly high entropy, theorized to be related to the information paradox and event horizons. But Preon stars, if they lack true event horizons, might carry entropy in ways we don't yet understand. They might store or radiate information differently, offering a way to resolve some of the deepest paradoxes in modern physics. Preon stars also demand we revisit the concept of mass itself. If mass is the manifestation of bound energy, and preons are smaller building blocks than quarks, then the mass-energy dynamics within a Preon star could be radically different. Perhaps their binding energy constitutes a majority of their mass, or perhaps they expose hidden asymmetries in the Standard Model that only appear under extreme compression. Even time behaves differently in the presence of such dense matter. A Preon star's gravitational time dilation would likely exceed that of a neutron star but fall just short of a black hole. This creates a bizarre environment where time passes dramatically slower near the surface than in space nearby. A hypothetical observer could experience minutes while years pass outside, similar to black holes, but without the infinite boundary. Some theories propose that these objects might also possess an incredibly small radius compared to their mass. A Preon star the mass of the Earth might have a radius of only a few millimeters, making it virtually impossible to detect through conventional means. Its gravitational pull, however, would remain immense. Such an object traveling through the solar system could subtly perturb the orbits of planets and spacecraft, acting like an invisible hand tugging on the fabric of space. The effects might be mistaken for anomalies or errors in measurement, unless carefully studied. This level of compactness raises fascinating questions about the possible gravitational effects of these stars. For example, microlensing, where a massive object bends the light from a background star, could be one of the few ways to identify them. But even microlensing events would be rare and fleeting for such small objects. The challenge would be to differentiate a microlensing event caused by a Preon star from one caused by a rogue planet or black hole. Their signatures might be slightly different due to the unique curvature of spacetime near such dense bodies. The search for Preon stars, therefore, might require a new generation of observational tools. Traditional telescopes may be of limited use, but gravitational wave detectors, space-based interferometers, or new kinds of particle detectors might be the key. We would need instruments capable of capturing incredibly subtle warps in space and time, or minute changes in gravitational fields. Perhaps even future quantum sensors will be sensitive enough to detect the passage of a Preon star near Earth, or reveal its presence in a distant galaxy. Another potential avenue for discovery lies in cosmic ray detection. Some theoretical physicists have proposed that Preon stars, when interacting with normal matter, could produce bursts of exotic particles, radiation that doesn't match any known decay pattern. These high-energy anomalies, detected as cosmic rays, might be rare but unmistakable. It's possible we've already seen hints of such events but simply lack the theoretical framework to interpret them as the footprint of a Preon star. The effects of a Preon star collision would be cataclysmic on a local scale, but possibly groundbreaking scientifically. If one were to collide with a neutron star or even pass close to one, the resulting interaction could produce shockwaves of gravitational and electromagnetic energy. The data from such an event might illuminate not just the existence of Preon stars, but also provide insights into the boundary between known physics and the undiscovered frontier. There's also speculation about how these stars might form. If they did not originate during the earliest moments of the universe, Could they arise from neutron stars collapsing further into Preon matter under extreme conditions? Perhaps a neutron star could reach a threshold density, beyond which the neutrons themselves break apart, releasing their Preon constituents and forming a denser, smaller object. This phase transition, if it occurs, would be one of the most extreme transformations of matter known in physics. If such a transformation is possible, it could redefine how we understand stellar evolution. The life cycle of massive stars might not end with neutron stars or black holes, but with something stranger still. We may need to redraw the evolutionary chart of stellar death to include a new branch, a descent into a realm of matter we've never directly observed. And if Preon stars are indeed a possible endpoint, their implications touch every part of cosmology, from entropy and information loss to the fundamental structure of reality itself. Preon stars also tie into the enduring mystery of the information paradox. Black holes are thought to destroy information, violating a principle of quantum mechanics. But if Preon stars can mimic black holes in terms of gravity without crossing the event horizon threshold, they might represent a loophole in this paradox. Information might not be lost, just compressed into a nearly inaccessible state. That opens the door to reconciling quantum theory and general relativity in a new and unexpected way. Moreover, their potential role in gamma-ray bursts is another fascinating avenue. Short gamma-ray bursts are powerful and enigmatic, often attributed to neutron star mergers or black hole collisions. But what if some of them are caused by Preon star activity? A collision or collapse involving Preon matter could release immense amounts of energy in the form of high-energy photons. These flashes would be brief, distant, and nearly impossible to trace, yet potentially distinct in frequency or afterglow. If we knew what to look for, we might begin identifying Preon candidates from past observations. Archives of gamma-ray data, gravitational wave recordings, and cosmic ray events might contain hidden evidence. We simply need the right theoretical lens to re-examine this data and reclassify the anomalies we've long dismissed as noise or unexplained events. This reinterpretation could lead to a quiet revolution in astrophysics. Despite their theoretical appeal, Preon stars remain controversial. Some physicists argue that the energies required to form Preon matter would be so extreme that no known mechanism could produce it naturally. Others maintain that even if preons exist, they might not be capable of forming stable structures on a macroscopic scale. Still, the history of science is filled with once dismissed ideas that became foundational. The notion of atoms, the existence of black holes, even the Big Bang theory itself, all faced skepticism before gaining acceptance. It's worth noting that the pursuit of Preon stars is not just about exotic astrophysics or elegant theory. It's about pushing the limits of what we know and daring to ask questions that challenge our assumptions. Even if Preon stars are never detected, the journey to seek them could lead to discoveries we never expected: new particles, new physics, new ways of seeing the universe. And if we do find them, we may finally begin to understand what matter really is at the most fundamental level. These kinds of interactions might even help explain some currently unexplained cosmic ray events. High-energy particles striking the Earth's atmosphere at inexplicable velocities, with trajectories that defy current understanding, might be the result of brief encounters with Preon-based matter. Such impacts might mimic other cosmic phenomena like gamma-ray bursts or pulsar emissions, but show subtle deviations in timing, energy distribution, or polarization. These clues could be buried within mountains of astrophysical data, waiting to be uncovered with more refined models and analysis techniques. Equally fascinating is the potential role Preon stars could play in the evolution of the cosmos. If they formed shortly after the Big Bang, they may have influenced the distribution of matter on large scales. Their extreme mass and compactness would allow them to act as gravitational seeds around which gas and dust could have accumulated, potentially guiding the formation of early galaxies or even acting as dark matter halos. The gravitational influence of an unseen population of Preon stars could help explain discrepancies between observed galactic motion and the distribution of visible matter. Moreover, their interaction, or lack thereof, with electromagnetic radiation means they would be almost invisible to telescopes, just like dark matter. If Preon stars neither emit nor reflect light, they would evade detection by traditional astronomical surveys. This property strengthens their candidacy as potential dark matter objects, or at least as components of a more complex dark sector. They could comprise part of what's called macroscopic dark matter, or individual, massive but compact objects make up a portion of the unseen mass of the universe. Another compelling question is whether Preon stars could form naturally today, or if they are exclusive relics of the early universe. If the conditions for their formation no longer exist, they might be incredibly rare, perhaps limited to a finite number created during a brief window when the universe was still in a highly energetic and exotic state. But if some astrophysical events, like the collisions of neutron stars or black holes, could compress matter to the necessary densities, then it's possible that Preon stars might still be forming, even now, in extreme environments. If such formations are indeed happening, they could be responsible for some of the most mysterious transient events observed by astronomers. Fast radio bursts, FRBs, for example, have puzzled researchers since their discovery. Some theories propose that these brief but intense flashes of radio waves could be generated by the collision or collapse of exotic objects, perhaps even Preon stars. A sudden restructuring of matter at subquark scales could unleash a burst of energy detectable across vast distances. The implications extend beyond just observational astronomy. If preons exist and can form stars, this would revolutionize particle physics. Our understanding of the Standard Model would have to be significantly revised or expanded. Preons would take their place as the true elementary particles, and quarks and leptons would be reclassified as composite objects. This would parallel the historical transition from atoms being considered indivisible to the realization that they consist of protons, neutrons, and electrons, and later that even those contain smaller constituents. This revised framework would impact everything from quantum field theory to cosmology. The mathematics used to describe particle interactions would need new terms and symmetries. Conservation laws, coupling constants, and decay processes would need to be re-evaluated. The entire framework for how particles acquire mass, charge, and spin might change, offering fresh insight into unresolved questions like the hierarchy problem or the nature of neutrino oscillations. Additionally, the potential for Preon stars to exist invites speculation about the extremes of matter. Could there be states of matter beyond even what we imagine in quark-gluon plasmas? Could preons themselves bind into different configurations, forming not only stars but perhaps entirely new phases of matter, preonic liquids, solids, or even crystalline structures at ultra-high densities? Such possibilities stretch the imagination but remain grounded in the logic of known physics extrapolated into the unknown. Even the gravitational behavior of Preon stars could provide new clues about spacetime itself. These objects might be ideal natural laboratories for testing the limits of general relativity and exploring quantum gravity. The curvature of spacetime near a Preon star could be more extreme than around a neutron star but still less than that of a black hole, creating a unique regime where current models are pushed to their limits. This could offer hints about how gravity behaves at ultra-small scales or how it might be unified with quantum mechanics. If observed directly, Preon stars might even help us resolve some of the universe's biggest mysteries, such as the true nature of singularities. If a collapsing star could form a Preon star instead of a black hole, it might avoid forming a singularity altogether. This could imply that nature has a built-in mechanism to prevent the infinite compression of matter, a concept that would radically alter our understanding of what happens inside black holes, or even if true black holes actually exist. The search for Preon stars opens the door to incredible new technologies. Understanding how matter behaves at such compact levels could lead to materials science breakthroughs, or even pave the way for energy extraction techniques far beyond nuclear fusion. The energy stored in subquark configurations could dwarf even the most powerful reactions known today, making it the next frontier of power generation, though likely centuries away from practical application. If it turns out that Preon stars can form even under modern cosmic conditions, their presence in the current epoch of the universe could be more widespread than previously imagined. The collapse of neutron stars under the right conditions, possibly triggered by extreme accretion, collisions, or exotic quantum tunneling effects, might lead to the birth of Preon stars today. These would be new additions to the cosmic landscape, potentially forming in the hearts of dense star clusters, near the centers of galaxies, or within the aftermath of catastrophic cosmic events. This possibility introduces a tantalizing idea that some of the compact objects currently identified as black holes might, in fact, be Preon stars. Black holes and Preon stars share similar properties in terms of mass and gravitational influence, but their internal structures would be radically different. If a black hole is a singularity shrouded by an event horizon, a Preon star might have a physical surface, albeit at densities beyond anything we've ever encountered. Detecting such a surface through precision measurements of gravitational waves or accretion behavior could provide the key to distinguishing between these two cosmic enigmas. The question of surface behavior becomes particularly important when analyzing how these objects interact with surrounding matter. A black hole swallows anything that crosses its event horizon, with no observable emission other than Hawking radiation. A Preon star, on the other hand, could emit bursts of radiation when matter strikes its surface, similar to how neutron stars produce X-ray flashes during accretion. Observing such signatures in places previously assumed to house black holes could point to the existence of an entirely new class of stellar remnant. Another factor to consider is the potential role of Preon stars in high-energy astrophysical phenomena. If they can collide with other stars or with each other, the resulting energy release might dwarf even the most violent supernovae or gamma-ray bursts. Such an event could flood space with gravitational waves, neutrinos, and exotic particles, producing a detectable signature that current and future observatories might catch. These collisions, while rare, would provide unprecedented laboratories for probing the fundamental forces of nature. In the realm of theoretical physics, Preon stars challenge our understanding of matter itself. If they are real, they demand that we revise the standard model of particle physics or develop entirely new frameworks. The forces binding preons together must be unimaginably strong, exceeding even the strong nuclear force that holds quarks within protons and neutrons. Such interactions would require new gauge fields, new symmetries, or even new dimensions, ideas that have been explored in various extensions of particle physics, such as string theory and grand unified theories. This leads to deeper philosophical implications. Preon stars might not just be exotic objects, they could represent a deeper layer of reality, suggesting that what we perceive as fundamental particles are in fact emergent structures built from even more elementary constituents. This Russian doll model of matter implies that nature has more layers yet to be revealed, and that our current knowledge is only scratching the surface of a vastly more complex cosmic architecture. If we one day confirm the existence of preons, it might unlock technologies previously confined to science fiction. Mastery over such dense states of matter could lead to advances in energy production, quantum computing, and materials science. Imagine being able to manipulate matter at such a fundamental level that entire elements, or energy states, could be engineered from scratch. This dream remains far off, but the path to such possibilities begins with understanding these mysterious stars. The observational hunt for Preon stars is difficult, but not impossible. Gravitational wave observatories like LIGO and Virgo could detect unusual waveforms from collisions involving objects smaller and denser than neutron stars. Radio telescopes might pick up strange pulsar-like emissions from isolated Preon stars rotating at incredible speeds. Infrared surveys could detect subtle gravitational lensing effects from invisible but massive objects passing in front of distant stars. And then there's the role of next-generation technology. The James Webb Space Telescope, along with future ground and space-based observatories, could provide unprecedented resolution in deep space. With better data and better models, astronomers might reanalyze existing anomalies and find evidence hiding in plain sight. Machine learning could assist in identifying patterns that human eyes might overlook, perhaps pointing us toward the signatures of Preon stars buried in terabytes of archival data. One intriguing target for such investigations could be the galactic center. This region teems with massive, compact objects and high-energy activity, making it a potential breeding ground for exotic stellar remnants. If Preon stars exist in any significant number, it's not unreasonable to expect at least a few to be lurking in that chaotic cosmic cauldron. Advanced simulations could help identify where to look and what kinds of signals would betray their presence. Even with all this theorizing, the scientific community remains cautious. Extraordinary claims require extraordinary evidence, and Preon stars are among the most extraordinary hypotheses in modern astrophysics. Confirming their existence would not only require detecting them but also ruling out all other plausible explanations for the observed phenomena. It would demand the convergence of multiple disciplines: astrophysics, particle physics, cosmology, and advanced mathematics, all working in harmony. Yet, it's precisely this challenge that makes the idea so compelling. Preon stars sit at the intersection of the unknown and the possible, daring us to question the limits of our knowledge. They are a cosmic riddle wrapped in quantum mystery, buried in the heart of some of the universe's darkest corners. And if they do exist, they might hold answers to questions we haven't even learned how to ask yet. Another factor to consider is the potential role of Preon stars in the cosmic energy budget. While black holes are considered endpoints of gravitational collapse, Preon stars would instead represent a form of equilibrium between gravitational forces and the degeneracy pressure of preons. This balance could allow them to remain stable for billions, perhaps trillions, of years. If even a small fraction of known black holes were actually Preon stars, this would alter our models of stellar death, compact object distribution, and the total energy stored in dense matter across the universe. Their lifespans, being possibly longer than the age of the universe, would make them ideal candidates for studying cosmological timelines. Unlike stars that evolve and die in cosmic short order, or black holes that slowly evaporate through Hawking radiation, Preon stars might serve as near-eternal relics, unchanged since their formation. Studying their gravitational influence, motion, and effects on nearby matter could effectively act as a time capsule, preserving the physical conditions and matter distributions from the era of their birth. There's also a speculative but fascinating hypothesis. Could Preon stars be artificial? In other words, might a sufficiently advanced alien civilization have found a way to manipulate matter at the subquark level, creating these hyperdense structures as energy sources, computational substrates, or even tools for manipulating spacetime? While such ideas are purely theoretical at this point, the mere possibility pushes the boundaries of both physics and our imagination. It raises the broader question of whether our current understanding of matter is sufficient to grasp the full complexity of the universe. If Preon stars are indeed a reality, and especially if they exist in significant numbers, then they may require a complete rewrite of our stellar classification system. For decades, astronomy has worked with a relatively straightforward sequence: white dwarfs, neutron stars, and black holes. Each of these corresponds to a progressively denser form of stellar remnant. Preon stars would introduce a new tier, representing the next step in this evolutionary hierarchy. Their addition would require not only new definitions, but new models of matter, new equations of state, and new frameworks for understanding gravity and quantum fields under extreme compression. This also poses serious questions for existing models of neutron star mergers. These high-energy collisions, observable through gravitational wave detectors like LIGO and Virgo, are assumed to produce either more massive neutron stars or black holes. But if the density threshold is crossed, it's possible they could instead create Preon stars. If even a single such event has already occurred in a way we misinterpreted, then some of the gravitational wave data collected over recent years may hold hidden signatures of Preon star formation. One area to explore is the gravitational waveform itself. Preon stars would likely produce a different signature than a black hole, due to differences in their internal composition and the way they absorb and emit energy. The sharpness of the wave, the tail of the merger, or even minor resonances post-merger could subtly differ. Analysts would need to revisit old waveforms and reprocess them using new models that factor in preonic matter as a potential end state. Such reanalysis might already be underway in some research circles, but confirmation would revolutionize our understanding of what's lurking in the gravitational shadows. Another intriguing angle lies in the magnetic field strengths of Preon stars. If they retain or even enhance the magnetic dynamo effects seen in neutron stars, Their fields could be unimaginably strong, far exceeding those of magnet Rs. These intense fields might interact with their environments in strange ways, perhaps creating ultra-high-energy jets, influencing nearby stars, or distorting the trajectories of charged particles over vast distances. Some observed cosmic phenomena with unclear magnetic origins might be explained by the presence of one or more Preon stars. Moreover, the surface of a Preon star, if such a thing exists in any classical sense, would likely behave in bizarre and exotic ways. Tidal forces near this surface would be extreme, tearing apart atoms and molecules into subcomponents before they even make contact. Time dilation would be severe, much like near the event horizon of a black hole, meaning that from an outside observer's perspective, events on or near the surface would occur incredibly slowly. This has implications for how we might observe these stars, making real-time observation of their dynamics almost impossible. If an accretion disk formed around a Preon star, it could potentially provide a diagnostic clue. The emission spectrum of this disk, particularly in X-rays or gamma rays, might show subtle deviations from those of known neutron stars or black holes. The inner radius of the disk could sit closer to the surface due to the lack of an event horizon, affecting orbital dynamics, heating rates, and luminosity. With the next generation of space telescopes, especially those capable of high-resolution spectroscopy, we might be able to detect these anomalies and infer the presence of a Preon star at the center. Preon stars might also redefine our understanding of compact binary systems. In some close-orbiting binaries, the compact object accretes material from a nearby companion, creating luminous and often variable emissions. If the compact object is a Preon star, its interactions with the accreted matter would differ significantly. The energy conversion efficiency, spin rate modulation, and frequency of emitted radiation might all deviate subtly from expectations, opening another path for indirect identification of these elusive entities. If Preon stars are indeed a reality, and especially if they exist in significant numbers, then they may require a complete rewrite of our stellar classification system. For decades, astronomy has worked with a relatively straightforward sequence, from main sequence stars to white dwarfs, neutron stars, and black holes. This framework has served as a cornerstone of astrophysics. But inserting Preon stars into this evolutionary chain introduces a new dimension. It suggests that after neutron stars, under even more extreme pressures and densities, there might be another transition, another tier of matter collapse not previously accounted for. This opens up a new category of ultra-compact stars that challenge what we thought were the upper boundaries of stellar evolution. The discovery of such an object would not just expand our cosmic catalog, it would force a fundamental reassessment of the limits of matter. Every known particle in the universe is subject to certain forces and rules, and up to now, the quark level has been considered the most elementary. The existence of Preon-based matter would imply that even the strongest of known nuclear forces, the strong interaction binding quarks together, can be overcome, and that there exists a still deeper substrate of matter with its own binding energy, stability constraints, and phase states. We would have to revisit all our models of mass, energy, and particle interaction from the ground up. The equations that describe the behavior of neutron stars rely heavily on nuclear physics and quantum chromodynamics. But Preon stars would require an entirely new theoretical framework, possibly based on an extended or alternative version of the standard model that incorporates subquark structures and interactions. The implications wouldn't just affect astrophysics. They would reach into particle physics, quantum theory, and even the nature of spacetime itself. It's worth noting that if Preon stars exist, they might have been detected already, only we lack the tools or theories to recognize them. Some ultra-compact objects currently categorized as small black holes may be misclassified. Their mass-to-radius ratios could closely resemble black holes, but without the telltale signs of event horizons or singularities. These objects may emit unique radiation signatures, respond to tidal forces differently, or rotate in a way that sets them apart. Precision studies of their spin rates, gravitational lensing patterns, and accretion disk behavior might reveal anomalies that can't be explained with existing models. Gravitational waves offer another potential window. When neutron stars collide, or when a neutron star merges with a black hole, the resulting gravitational wave signal tells a story. If a Preon star were to collide with another dense object, the resulting waveform could be subtly distinct. The resonance frequencies, damping times, and peak amplitudes might reveal the object's true nature. Already, observatories like LIGO and Virgo have opened up the field of gravitational wave astronomy, and as sensitivity improves, it's possible that Preon stars could be identified through deviations from expected merger profiles. We should also consider the role of Preon stars in cosmological evolution. If they formed in the early universe, they might serve as seeds for galaxy formation, just as supermassive black holes do. Their immense density would allow them to gravitationally attract massive clouds of gas, influencing the structure of early galaxies. Unlike black holes, however, Preon stars may not consume matter in the same irreversible way. This could lead to unique galactic dynamics, star formation rates, and central mass distributions that differ from those we observe around black holes. The implications extend even to dark matter. One of the greatest mysteries in physics is the nature of the invisible matter that makes up most of the universe's mass. While many candidates have been proposed, WIMPs, axions, sterile neutrinos, none have been confirmed. Preon stars, if abundant and electromagnetically dark, could contribute significantly to the dark matter profile. Their compactness would allow them to pass through galaxies without disrupting normal matter, and their gravitational effects could help explain the rotational curves of galaxies and gravitational lensing anomalies. Furthermore, Preon matter might itself be a form of dark matter in certain states. If stable Preon particles exist, they might roam the cosmos in diffuse clouds, or cluster into non-luminous objects that are incredibly hard to detect. Their lack of electromagnetic interaction would make them effectively invisible to traditional telescopes, while their gravitational pull could influence structure formation across the universe. This dual identity, both as compact stars and diffuse particles, makes Preon matter a highly compelling dark matter candidate. On the thermodynamic front, Preon stars raise profound questions about entropy, heat flow, and internal structure. The conditions inside these objects would be orders of magnitude beyond those inside neutron stars. The equations of state that apply to neutron matter break down completely at these densities. Would the interior of a Preon star resemble a quark-gluon plasma frozen into solid form? Would there be distinct layers or phases, like the crust and core of a neutron star? Or would the entire body be a uniform superfluid of preonic material, possibly exhibiting superconductivity and zero viscosity? We must also consider how these objects would respond to extreme external stimuli. What happens if two Preon stars collide? Would they merge into a larger object, collapse into a black hole, or perhaps even explode in a new kind of hypernova? Such a collision could release unimaginable energy, possibly even creating gravitational wave events stronger than anything we've yet observed. These cataclysmic events might serve as natural particle accelerators, producing exotic byproducts like strangelets, tachyons, or unknown forms of radiation. Then there's the question of survivability. Could Preon stars form a long-lasting equilibrium, or are they inherently unstable? If even a slight disturbance, such as tidal forces from a nearby black hole, could trigger collapse or explosion, then the presence of Preon stars would introduce a layer of cosmic volatility not previously accounted for. Their stability would depend on the nature of the preonic binding force, which remains theoretical. If that force is strong enough to resist collapse, these stars might endure for eons. If not, they might be ticking time bombs. In a broader sense, the existence of Preon stars would challenge humanity's deepest assumptions about the universe. For centuries, we've peeled back layer after layer of the cosmos, discovering atoms, then nuclei, then quarks. Each time, we thought we had reached the end. Preons represent yet another layer, and if they give rise to stable structures like stars, then the universe is more intricate than we dared to dream. It reminds us that nature may be infinitely recursive, with each answer revealing a deeper question, each discovery exposing a deeper mystery. If preons exist, and if they form the basis for a new class of compact stars, then the early universe might have been a far more complex and turbulent place than we've previously assumed. During the first microseconds after the Big Bang, matter was in a highly energetic and chaotic state, conditions that could have permitted the formation of Preon stars alongside or even before the formation of baryonic matter. That means these objects might be among the oldest entities in the universe, relics from a time before atoms, before nuclei, even before quarks dominated the cosmos. Their formation during such an early stage of the universe could have significant implications for the large-scale structure we observe today. If Preon stars formed in abundance, their gravitational effects could have seeded the initial clumping of matter into galaxies, clusters, and filaments. Even in small numbers, they could have acted as gravitational anchors that influenced the motion of dark matter and ordinary matter alike. Over billions of years, their subtle influence could have shaped the very architecture of the cosmos. And if they truly are that ancient and long-lived, they might still be lurking in the depths of space, largely undetectable due to their small size and lack of emitted radiation. This makes them excellent candidates for the elusive, dark, components of the universe. While dark matter has never been directly observed, and its composition remains one of the biggest open questions in modern science, Preon stars, dense, massive, non-luminous, and stable, could easily account for at least part of that invisible matter if they exist in sufficient numbers. To detect something so elusive, scientists are exploring alternative observational techniques. Traditional telescopes that rely on light, optical, infrared, or even X-ray, would likely miss Preon stars entirely. Instead, astronomers may need to rely on indirect signatures, gravitational lensing, tiny but measurable distortions in the light from distant galaxies caused by massive objects along the line of sight. Even small Preon stars could bend light enough to produce these effects, particularly if they pass in front of background stars. Another promising avenue involves gravitational wave detectors. If two Preon stars were to collide or spiral into each other, they would generate ripples in spacetime, much like black holes or neutron stars do. But because Preon stars would be denser and smaller, the waveform of their merger would differ significantly, producing a high-frequency, short-duration burst that could be distinguishable from other cosmic events. By studying such signals, scientists might be able to confirm the existence of Preon-based matter. In theory, a close encounter between a Preon star and another object, such as a neutron star or a black hole, might also produce unique high-energy phenomena. As matter from one object is stripped away or compressed, we might observe unusual gamma-ray bursts or anomalous neutrino emissions, inconsistent with current models. These peculiar signatures could serve as breadcrumbs leading us to the first confirmed identification of a Preon star. The very existence of such objects would push our particle physics into uncharted territory. For decades, the standard model has been the reigning theory, describing all known fundamental particles and their interactions. But preons, as hypothetical subcomponents of quarks and leptons, would represent a deeper level of structure. This would require either an expansion of the standard model or a completely new theoretical framework, one that unifies gravity with quantum mechanics and perhaps even incorporates extra dimensions or exotic symmetries. Such a shift would not be unprecedented. History is filled with moments where the prevailing model of physics had to be overhauled in light of new evidence, from Newtonian mechanics to relativity, from classical physics to quantum theory. If preons are real, we may be on the cusp of the next major scientific revolution. And Preon stars, as macroscopic manifestations of this new particle layer, would serve as the beacons guiding us into that next frontier. There's also a philosophical implication here. Preon stars challenge the notion of indivisibility. For centuries, science has been a journey downward, to ever smaller scales, uncovering the building blocks of reality. First molecules, then atoms, then protons and neutrons, then quarks. If preons exist, they might not be the end of that road either. Could there be something even smaller than preons? A kind of infinite regress into substructure? Or is there a true fundamental layer where nature finally stops? This question doesn't only affect physics, it touches on the very nature of existence. If everything we know, from the largest galaxies to the smallest particles, is composed of layers upon layers of structure, each one nesting within another, then perhaps the universe itself is not a simple construct but a fractal-like tapestry of complexity, extending in both directions, out toward the cosmic scale and inward toward the unimaginable small. Such a view encourages a sense of humility. Even with all our telescopes, satellites, and particle colliders, we might still be infants in our understanding of the cosmos. We often assume that the universe operates on scales and principles we can comprehend. But Preon stars remind us that there may be entire classes of objects, entire realms of physical law, still hidden from our senses. Their discovery would be a sobering but exhilarating reminder of how much we have yet to learn. To detect something so elusive, scientists are exploring alternative observational techniques. Traditional telescopes that rely on light, whether visible, radio, or X-ray, are of limited use when it comes to Preon stars. These hypothetical objects may not emit electromagnetic radiation in any measurable way. They wouldn't shine, pulse, or flare like their neutron star counterparts. Instead, their presence would be betrayed by the influence they exert on surrounding matter and space-time. This shifts the burden of detection to gravitational effects, something that modern astrophysics is only just beginning to master through gravitational lensing and wave detection. Gravitational lensing occurs when a massive object bends the light from a more distant source behind it, creating a warped or magnified image. It's a technique already used to find exoplanets and dark matter concentrations. If a Preon star were to pass in front of a distant light source, it might cause a subtle, but measurable, lensing event. The challenge is that these events are incredibly brief and rare, and the lensing effect from a Preon star might be very small. Still, with the increasing sensitivity of space-based observatories and sky surveys, such as those conducted by the Vera C. Rubin Observatory or the upcoming Nancy Grace Roman Space Telescope, the chances of catching these fleeting events are improving. Another possibility lies in gravitational waves. When massive objects accelerate, such as during the collision or orbit of compact stars, they create ripples in spacetime that propagate outward at the speed of light. These waves were first directly detected in 2015, confirming a major prediction of Einstein's general relativity. If Preon stars collide or merge with each other, or with neutron stars or black holes, the resulting gravitational waves might have a distinct signature, different from the mergers we've already detected. By analyzing waveforms in extraordinary detail, physicists might be able to isolate the unique fingerprint of a Preon star event. Still, it's not only through gravitational phenomena that Preon stars might be revealed. There could be indirect electromagnetic signatures produced by their interactions with other cosmic objects. For instance, if a Preon star were to accrete matter from a companion star or pass through a dense gas cloud, it might briefly emit radiation, not because of any internal processes, but due to the heated external material. These emissions could appear in gamma or X-ray wavelengths, much like black hole accretion disks, but with subtle differences that would stand out upon close analysis. Astrophysicists also entertain the possibility that Preon stars could disrupt their surroundings in subtle but measurable ways. For example, a Preon star moving through a dense star cluster might gravitationally perturb the orbits of nearby stars. These orbital anomalies could be observed and analyzed over time to infer the presence of an unseen massive object. While not conclusive on their own, patterns of unexplained stellar motion across multiple systems might build a compelling case. If any such anomalies were found near the cores of galaxies or globular clusters, they might point to populations of ultra-compact objects that aren't accounted for by black hole or neutron star models. Especially if these anomalies occur without accompanying electromagnetic signatures, scientists might begin to suspect that something stranger, something even denser and more exotic, was at play. The potential interactions between Preon stars and dark matter are also a tantalizing area of research. If Preon stars are stable and interact only gravitationally, they might behave in ways nearly indistinguishable from cold dark matter. However, if they have even minimal non-gravitational interactions, perhaps through a very weak residual force, they might cluster differently, or reveal themselves through collisions, or even decay processes on vast timescales. These possibilities are speculative, but they offer one of the most exciting paths forward in the hunt for both dark matter and new forms of matter itself. We must also consider the possibility of Preon stars existing in binary systems, orbiting one another or partnered with more conventional stars. Such systems are laboratories of extreme physics, allowing for detailed timing and observational studies. The discovery of a binary system involving a suspected Preon star could be revolutionary. Through precise measurements of orbital decay, relativistic effects, and perhaps periodic bursts or emissions, astronomers might gather enough evidence to confirm or refute their nature. While no confirmed detection of a Preon star has occurred as of yet, the sheer number of unexplained gravitational phenomena in the universe leaves the door wide open. Fast radio bursts, for instance, intense, brief pulses of radio waves from distant galaxies, remain one of the most mysterious phenomena in astronomy. Some scientists have speculated that these could be caused by interactions involving exotic compact objects. Though most models still favor neutron stars or magnetars as the culprits, the door is not closed to alternatives like Preon stars, especially as our data grows. Preon stars also raise deep philosophical questions about the limits of reductionism in physics. If quarks are not fundamental, and if they themselves are composed of smaller units, then our entire understanding of the particle zoo needs to be revised. The concept of elementary particles becomes more of a placeholder than a fundamental truth. Each new layer we peel back may only reveal yet another, more mysterious foundation beneath. This process mirrors the historical journey of science. At one time, atoms were thought to be indivisible. Then came the discovery of electrons, protons, and neutrons. Later, quarks and leptons took their place as the building blocks of the universe. If preons exist, they would continue this pattern, suggesting that nature may never bottom out at a truly fundamental level. Instead, the universe might be a fractal of deeper and deeper structures, each giving rise to the one above. They would produce a unique gravitational wave signature that could potentially be detected by observatories like LIGO, Virgo, or CAGRA. Unlike typical neutron star or black hole mergers, the waveform from a Preon star collision might differ in amplitude, frequency, and decay pattern. Scientists would need to identify and catalog such anomalies to isolate them from more common astrophysical events. In the future, the development of more advanced detectors, such as the planned space-based LISA, Laser Interferometer Space Antenna, could open new possibilities for detecting even fainter or more exotic gravitational events, increasing the chance of discovering Preon stars if they exist. Another approach involves examining anomalies in the motion of stars within galaxies. If Preon stars make up a portion of dark matter, they would contribute to the gravitational mass of galaxies without emitting light. Detailed star mapping missions, such as Gaia, allow astronomers to chart the motion of millions of stars with extreme precision. By analyzing subtle deviations from expected trajectories, researchers might be able to infer the presence of compact, dark masses like Preon stars hiding in the galactic halo or drifting through interstellar space. The theoretical modeling of Preon stars also extends into the realm of high-energy particle physics. Physicists are actively working to refine models that describe how preons would interact, bind, and behave under extreme pressures and temperatures. This involves extending the standard model or developing entirely new frameworks. Some proposed theories suggest that preons could be tied to supersymmetry, extra dimensions, or even aspects of string theory. If Preon stars exist, their internal structure could hold the key to unifying the forces of nature or explaining why the universe has the particle diversity we observe today. One critical feature of Preon star theories is their predicted density. These objects would be vastly denser than neutron stars, possibly by several orders of magnitude. A single teaspoon of Preon star matter might weigh more than Mount Everest. This incredible density implies that such stars would have a correspondingly small radius and gravitational field strong enough to warp space in extreme ways, though not quite collapsing into a black hole. This delicate balance between gravitational collapse and internal pressure from degenerate Preon matter could provide valuable insights into the limits of matter compression. Preon stars might also exist in different configurations depending on their formation history, mass, and internal pressure. Some theories suggest that they could be stable in various mass ranges, some similar to asteroids, others comparable to small stars. This diversity would mean that we might be looking for a whole population of different-sized compact objects that defy standard classification. Detecting even one of them could upend our understanding of stellar evolution and cosmic composition. In some models, the existence of Preon stars could help explain certain astrophysical anomalies. For example, some gamma-ray bursts and fast radio bursts have durations, intensities, or frequencies that don't fit neatly within known models involving neutron stars or black holes. These strange outbursts might be the result of interactions involving Preon stars, perhaps collisions, collapses, or exotic phase transitions within their ultra-dense cores. Future research may reveal whether these unexplained phenomena are linked to such exotic objects. There's also the tantalizing idea that Preon stars could interact weakly with normal matter, similar to how dark matter is thought to behave. If they pass through planets or stars, they might leave behind subtle disturbances or energy losses. Some researchers have proposed looking for transient events, like localized gravitational anomalies or unexplained seismic activity on Earth and other celestial bodies. While extremely speculative, these approaches highlight the imaginative lengths scientists are willing to go to when probing the limits of known physics. Despite the lack of direct evidence, the pursuit of Preon stars continues to fuel deep philosophical questions. What is the true nature of matter? Is there a final, indivisible layer to reality, or does the onion of particle physics have yet another layer beyond quarks? Could we, one day, harness the power of Preon matter for technology, just as we've harnessed atoms and electrons for modern life? These questions inspire the ongoing work of theorists and experimentalists alike. In the laboratory, efforts to detect subquark particles or phenomena consistent with Preon-like behavior are also ongoing. High-energy particle accelerators, such as those at CERN, are constantly pushing the boundaries of collision energies to search for deviations from the standard model. Any discovery of anomalous scattering events, unexpected particle decay patterns, or missing energy signatures could provide indirect evidence of Preon structures. While we haven't seen such signals yet, the possibility remains open. And then there's the universe itself, acting as a natural particle accelerator. In the highest energy environments, such as near black holes, during supernovae, or in the early moments after the Big Bang, conditions might arise that favor the creation or exposure of Preon matter. Studying cosmic rays, background radiation, and relic signatures from the early universe could reveal hints of their presence. Just as neutrinos were once elusive, yet now routinely detected, preons, or the stars they form, may one day shift from hypothetical to confirmed reality. Preon stars might also play a role in the early universe. Shortly after the Big Bang, when the cosmos was an extremely hot and dense plasma of fundamental particles, the conditions could have been just right for Preon matter to form temporarily before coalescing into more familiar particles like quarks and leptons. If preons are indeed more fundamental, their momentary dominance in the early universe could have left subtle imprints on cosmic structures, background radiation, or even the distribution of matter we observe today. Studying these patterns with next-generation telescopes and cosmic background analyzers could help detect signs of this early Preon phase, if it occurred. Furthermore, Preon stars challenge the boundaries of what we consider a star, in the traditional astrophysical sense. Unlike stars that shine due to nuclear fusion, or neutron stars that are remnants of collapsed stellar cores, Preon stars would not emit light in any visible spectrum. They would be utterly dark, almost undetectable unless they interacted with other matter or affected their surroundings gravitationally. This opens up the possibility that many Preon stars could be roaming the universe, completely unnoticed, silently shaping galaxies and cosmic filaments. Astrophysicists have begun modeling how Preon stars might interact with their environment, especially if they pass through clouds of interstellar gas or collide with other compact objects. Some scenarios suggest that such collisions could result in bursts of high-energy particles or even brief flashes of gamma rays, anomalous events that might already be recorded in astronomical data but misclassified due to our current lack of understanding. Future reanalysis of unexplained astrophysical bursts could potentially reveal clues pointing back to Preon star origins. The gravitational pull of a Preon star would be immense. Due to their extraordinary density, Even a Preon star the size of a pebble could outweigh an entire mountain. This compactness means that any object venturing too close would be subject to extreme tidal forces, potentially ripped apart before even reaching the star's surface. Simulations of such tidal interactions have provided some insight into how nearby matter might behave, and in doing so, help researchers identify unique gravitational signatures that differ from black holes or neutron stars. If Preon stars are real, they may help solve several lingering astrophysical puzzles. For instance, the core collapse problem in supernovae. Why some stars fail to go supernova despite expectations might be explained if the core collapses not into a neutron star or black hole, but into a stable Preon star instead. This would create a quiet, dark object that doesn't release the expected energy burst, which could account for certain observations of failed supernovae, where a star simply vanishes without a trace. In terms of composition, a Preon star would be radically different from anything we know. Rather than being made of atoms or even quarks, it would consist of bound systems of preons, particles that, by some theories, are orders of magnitude smaller than quarks. These hypothetical particles would be held together by a new type of force, sometimes referred to as a hypercolor force, operating at energy scales far beyond anything achievable with modern particle accelerators. Understanding this force could open new branches of physics and possibly answer questions about the true nature of matter. Some researchers have proposed that Preon stars could exist in various configurations, much like atoms have isotopes. These variations could differ in mass, charge distribution, or even stability. If such variations exist, they could account for the diversity of dark matter behaviors observed across the universe, from galaxy rotation curves to the movement of large-scale structures. In essence, Preon stars could offer a unifying explanation for phenomena that currently require multiple models or assumptions. From a technological standpoint, the discovery of a Preon star would be groundbreaking. If humanity could ever approach or interact with such an object safely, a far-fetched idea at our current level of technology, it might offer exotic applications. For instance, the dense matter within could be harnessed for unprecedented energy storage, or perhaps used in quantum computing due to its exotic states. Though speculative, the possibilities are enough to ignite imagination and fuel further research into the very real science behind the theory. Philosophically, the existence of Preon stars would prompt a re-evaluation of our understanding of simplicity in nature. We've long sought a unified, elegant explanation for the universe's complexity. The discovery of preons, and their organization into stable ultradense objects, would show that deeper layers of structure lie beneath what we've accepted as fundamental. It would underscore how little we still know, and how much more there is to uncover about the building blocks of reality. The mere pursuit of Preon stars, even before their discovery, is a testament to human curiosity and the relentless drive to understand the universe. By chasing shadows, decoding anomalies, and imagining the unimaginable, scientists continue a tradition as old as humanity itself. Preon stars might still be theoretical, but they represent the edge of the known, the doorway to what lies beyond, and perhaps the next great leap in our cosmic understanding. If Preon stars indeed exist and interact in such dramatic ways, they could help solve several cosmic mysteries that remain unresolved. For instance, one of the most perplexing puzzles in astrophysics is the nature of fast radio bursts, short, intense pulses of radio waves that originate from distant galaxies and defy conventional explanation. Some theories have speculated that the collision or sudden collapse of exotic objects like Preon stars could produce such bursts, providing a natural mechanism for the immense energy release over incredibly short durations. Preon stars could also have implications for understanding the ultimate fate of matter under extreme gravity. While black holes are traditionally viewed as the final state of matter collapse, introducing Preon stars into the picture offers an alternative. Perhaps some objects we assume are black holes are instead ultra-compact Preon stars that don't form event horizons but mimic the mass and gravitational pull of black holes almost perfectly. This possibility has stirred interest in revisiting past observations to look for discrepancies in expected black hole behavior, discrepancies that might support the existence of a dense, horizonless core instead. This horizonless nature is crucial. If Preon stars are more compact than neutron stars but not dense enough to collapse into black holes, they may represent a new equilibrium point in the universe's hierarchy of matter. Understanding that balance would require revolutionary physics, possibly even requiring modifications to general relativity or quantum field theory. These stars might even exhibit quantum gravitational effects on macroscopic scales, something never observed before but long predicted by theories attempting to unify quantum mechanics with gravity. Moreover, if Preon stars exist, they raise philosophical and existential questions about our place in the cosmos. Human understanding of matter has evolved from atoms to subatomic particles to quarks, and now potentially to preons. This suggests an endless fractal-like depth to the universe, where every layer reveals a deeper one beneath. Preon stars would not just be astrophysical anomalies but cosmic reminders of how much remains hidden beneath our current models and frameworks. There's also an intriguing possibility that preon matter could be stable enough to form structures beyond stars. Just as normal matter forms planets, moons, and complex systems, preon matter might do the same, only on a scale and in conditions vastly different from what we can currently imagine. Could there be preon planets? Or even preon-based life, operating under laws of chemistry and physics radically alien to us? While this idea borders on the speculative, science often begins with wild theories that slowly gather evidence and credibility over time. On the technological frontier, if humanity could someday harness or create preon matter, the implications for energy and engineering would be transformative. The energy density of preon material, if it reflects even a fraction of what theories predict, would dwarf anything possible with nuclear fusion or antimatter. Entire civilizations could be powered by grams of preon substance. However, the containment, manipulation, and ethical considerations of using such exotic matter would require a whole new paradigm in materials science and energy policy. In terms of detection strategies, one proposed method is microlensing, where the gravitational field of a compact object bends and magnifies the light of a more distant background star. This technique has already been used to identify exoplanets and dark objects like rogue black holes. If a preon star passes in front of a distant star, it could cause a unique lensing effect due to its density and size, allowing astronomers to infer its presence even if it emits no light at all. High-resolution and continuous sky surveys could help catch such rare but telling events. Collaborative efforts between particle physicists, astrophysicists, and cosmologists are becoming increasingly important in exploring preon star theories. No single discipline can fully address the multifaceted challenges involved. Particle accelerators might help simulate conditions approaching those inside preon stars. Meanwhile, astronomers refine their techniques to detect compact dark objects, and cosmologists work to reconcile early universe models with current observations. This interdisciplinary fusion could eventually provide a breakthrough in confirming or ruling out the existence of preon stars. It's also worth noting the role of computational modeling in advancing our understanding of these hypothetical objects. Supercomputers can simulate the behavior of quark-gluon plasmas, neutron-star mergers, and gravitational wave patterns. By tweaking these models to include hypothetical preon interactions, scientists can predict observational signatures to look for. These simulations can run thousands of scenarios, helping to narrow down what astronomers should be watching for in real sky data. The search for preon stars is part of a broader trend in physics, the drive to move beyond the standard model. While the standard model has successfully explained many particle interactions, it leaves questions unanswered, such as the nature of dark matter, the cause of matter-antimatter asymmetry, and the unification of gravity with quantum forces. If preons exist and preon stars are real, they could provide the critical missing piece that pushes physics into a new golden age of discovery and understanding. Preon stars, as hypothetical as they are, encapsulate this idea perfectly. Their existence would mean that the universe is far more intricate than our current models suggest. The very notion that matter might not be fundamental, even at the level of quarks and leptons, forces us to confront a new tier of the physical world, one where the smallest known components are merely the visible tip of a much deeper, hidden iceberg. This challenges long-held assumptions and encourages a new generation of theoretical models to explain what lies beneath. The implications for particle physics are staggering. If preons are real, then the Standard Model, the framework that currently describes all known particles and their interactions, would need to be revised or even replaced. Such a revision would require a new layer of mathematical structure to describe how preons interact, bind together, and form the building blocks of quarks and leptons. This would be nothing short of a scientific revolution, akin to the transition from Newtonian physics to Einstein's theory of relativity. In practical terms, discovering preons would transform high-energy physics. Particle accelerators like the Large Hadron Collider, which currently probe the interactions of quarks and leptons, would need to reach even higher energies to smash particles apart and expose their preonic substructure. Future colliders, perhaps operating at energy scales far beyond our current capabilities, might be designed with this exact goal in mind. The funding, engineering, and international cooperation required would be monumental, but the payoff, peering into the true foundation of matter, would be historic. One exciting consequence of a successful preon model would be the unification of forces. Physicists have long sought to unify the fundamental interactions, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single elegant theory. Preons, by offering a simpler basis for all known particles, could serve as the unifying language. Instead of treating each fundamental particle as unique, preons might reveal that all particles are variations of the same underlying patterns, shaped by the dynamics of preon interactions in multidimensional space. Theoretical physicists have proposed various models to describe how preons might behave. Some suggest they are confined by a new kind of strong force, stronger than the one that binds quarks inside protons and neutrons. Others speculate that preons exist in higher dimensional space, with our familiar four-dimensional universe, 3 of space and 1 of time, being just a shadow of a richer, hidden geometry. In such models, Preon stars might not just be ultra-dense but also hyperdimensional, objects that leak gravity or other effects into dimensions we cannot directly perceive. This opens up the tantalizing idea that Preon stars could be gateways to new physics. Their behavior might reveal phenomena that contradict classical expectations, such as violations of energy conservation in localized regions, anomalous gravitational lensing, or even time dilation effects that differ from those predicted by general relativity. Observing such deviations would not only confirm the existence of preon matter but also challenge our understanding of spacetime itself. Astrobiologists have even speculated, albeit in extremely speculative terms, that if preon stars are common and stable, they might host conditions for exotic forms of life or intelligence that operate on subatomic scales. While this stretches current science to its limits, it does reflect how radically our worldview would change if preons were proven to exist. Life, consciousness, and complexity might not be confined to the atomic scale we are familiar with, but could arise in entirely different physical regimes, governed by different rules. Another practical consideration involves the detection of gravitational waves. The collision or merger of preon stars would release immense gravitational energy. Unlike black hole mergers, which produce smooth and predictable waveforms, preon star mergers might produce jagged, erratic, or rapidly decaying signals due to their more complex internal structures. This could help distinguish them from known compact objects using data from gravitational wave observatories like LIGO and Virgo. Anomalous signals in existing data could already hint at such exotic events. Researchers have also begun simulating the internal composition of preon stars. Using supercomputers and advanced field equations, scientists can model how such stars might resist gravitational collapse. These models suggest that preon matter could be more rigid and incompressible than any known substance, supporting immense gravitational pressure without forming a singularity. This could allow preon stars to reach densities even greater than neutron stars while still maintaining a finite size and surface. Their immense gravitational fields could also affect nearby matter in strange ways. If a preon star were to pass through a dense region of gas or a stellar system, its gravity could distort, or even consume nearby objects without emitting light. Such a scenario might explain certain high-mass, dark phenomena observed in distant galaxies, regions where matter behaves as though influenced by invisible forces, but where no corresponding luminous object is found. In cosmic terms, Preon stars might serve as a bridge between the macro and micro scales of the universe. They would embody both the unimaginable density of the quantum world and the massive gravitational influence of celestial bodies. By studying them, we might finally begin to answer one of the greatest open questions in science: how gravity and quantum mechanics can be unified into a single coherent framework. A theory of everything that has eluded physicists for over a century. From a philosophical standpoint, the discovery of Preon stars would reaffirm a humbling truth: that the universe is always deeper than we assume. Just when humanity believes it has reached the limits of understanding, nature reveals a new layer of complexity. Preon stars, in this sense, are not just theoretical objects, they are metaphors for our endless quest for knowledge. They remind us that every answer leads to new questions and that the journey into the unknown is far from over. The unification of the fundamental forces has been one of the most elusive and captivating pursuits in modern physics. If preons exist, they may provide the missing link that allows physicists to bridge the gap between these seemingly distinct forces. The idea is that at incredibly high energies, far beyond those achieved in current particle accelerators, the differences between the forces begin to dissolve. In such an environment, preonic interactions could be governed by a single force, revealing a symmetry that has been broken as the universe cooled after the Big Bang. This potential symmetry might also explain the quantization of electric charge, the specific masses of known particles, and the apparent replication of particle generations in the Standard Model. At present, we observe that quarks and leptons come in three families, but we don't fully understand why this is the case. If all of these particles are made of different configurations of a small number of preons, then the complex family structure might be the result of simple variations in preonic binding. That would mean nature is not fundamentally complex. It only appears that way at higher levels of organization. Such a breakthrough would be transformative, not only for particle physics but also for cosmology. Preons might have played a vital role in the early universe, long before atoms, stars, or even quarks existed. In the first trillionth of a second after the Big Bang, temperatures and energies were unimaginably high, possibly high enough for preons to exist freely. As the universe expanded and cooled, these preons could have bound together to form quarks and leptons, kickstarting the formation of matter as we know it. This period, currently inaccessible to direct observation, might one day be reconstructed through the lens of preon theory. If we assume that preons are real, then preon stars become a logical, if speculative, consequence. These hypothetical objects would be even denser than neutron stars or quark stars, composed entirely of matter compressed to the level where quarks themselves have broken down into their preonic components. This extreme compression would require immense gravitational forces, likely resulting from the collapse of extraordinarily massive stars or the merger of dense objects in binary systems. The resulting object would be small, perhaps only a few kilometers in diameter, but so dense that a single teaspoon would weigh more than all the water in Earth's oceans. One of the most intriguing aspects of preon stars is their potential stability. Unlike black holes, which collapse to a singularity and are bounded by an event horizon, preon stars might resist further collapse. The internal pressure from preonic degeneracy, similar in concept to the degeneracy pressure in white dwarfs and neutron stars, could balance the gravitational force, creating a stable object that doesn't emit light and yet doesn't disappear into a black hole. Such an object would be almost invisible, detectable only through gravitational lensing or its interactions with nearby matter. This leads to a tantalizing possibility. Preon stars might already exist in the universe, hidden in plain sight. They might be masquerading as small black holes or contributing to the mysterious gravitational anomalies we attribute to dark matter. If they are sufficiently numerous, preon stars could even make up a portion of the universe's dark matter content. This would explain why dark matter interacts gravitationally but not electromagnetically. It could be composed of ultra-dense, cold, non-luminous objects that are nearly impossible to detect with traditional telescopes. The search for such objects is challenging, but not impossible. One method involves looking for microlensing events, where the gravitational field of a massive, invisible object passes in front of a distant star and temporarily magnifies its light. These microlensing events have been observed before, and while many are attributed to known phenomena, a few remain unexplained. A Preon star, passing between us and a distant star, could produce a unique lensing signature, one that differs subtly from that of a black hole or neutron star due to its compact size and potentially exotic mass distribution. Astrophysicists have also considered how Preon stars might affect their surroundings. If located in a binary system with a normal star, a Preon star could pull material from its companion, creating an accretion disk. The resulting X-ray emissions might mimic those of black holes or neutron stars, but with peculiarities that defy current models. Unusual rotation speeds, unexpected radiation signatures, or deviations in orbital behavior might serve as indirect evidence for a Preon star's presence. Detecting and interpreting such anomalies would require careful observation and a willingness to entertain alternative explanations. Another possibility is that Preon stars might occasionally collide with other compact objects, such as neutron stars or black holes. These cataclysmic collisions would produce gravitational waves, ripples in spacetime that travel across the universe. LIGO and Virgo, the current gravitational wave detectors, have already detected mergers between black holes and neutron stars. A Preon star collision might produce a wave pattern that's different in form or strength. As gravitational wave detection technology advances, it may become possible to distinguish these unique signatures from the background noise. In fact, theoretical physicists are already developing models to predict what a Preon star collision would look like in the gravitational wave spectrum. These models take into account the expected mass, density, and internal structure of Preon stars, and simulate the dynamics of the merger process. Comparing the simulated waveforms to actual observational data might yield a match, thereby providing the first indirect evidence of Preon stars. Even if such an event hasn't been seen yet, ongoing improvements in sensitivity and data analysis could bring us closer to this discovery. The ripple effects of confirming Preon stars would extend far beyond astrophysics. It would reshape our understanding of matter, energy, and the very structure of the universe. It could impact fields like quantum field theory, string theory, and cosmology, offering new constraints and possibilities. It might even change how we think about the beginning and fate of the universe itself. Preon stars would not just be new celestial objects, they would be a key to unlocking deeper truths about everything that exists. And most profoundly, Preon stars would remind us that the cosmos is still full of mystery. For all our telescopes, colliders, and mathematical models, we remain explorers in an infinite sea of unknowns. Each new discovery opens a door to another set of questions, and the search for Preon stars is one of the boldest journeys we can undertake. In chasing them, we are not just trying to understand distant corners of space. We are reaching for the very foundation of reality itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.